Picture something that's in nearly every car, looks ordinary and goes unnoticed, yet contains heavy metal, acid, plastic, and massive industrial potential. A car battery isn't just a box that starts your engine. It's one of the most valuable and simultaneously dangerous types of mass industrial waste. Toss it like regular trash and it becomes a pollution source, but send it through proper recycling and it becomes an example of almost perfect industrial circularity. Because an old battery can be disassembled, its lead separated, its electrolyte neutralized, its plastic returned to manufacturing, and much of its content transformed back into new batteries. That's why car battery recycling is considered one of the most closed-loop and efficient recycling systems in industry. Today, we'll break down how this process works, why it demands strict control, how hazardous waste becomes new raw material, and why an old battery isn't really trash at all, but an almost ready-made feedstock for the next production cycle. It all starts before the factory, at the collection stage. Used lead-acid batteries come back from repair shops, retailers, transportation companies, and collection centers, kept separate from regular waste. This is crucial because a battery can't go into general trash. Inside are lead components, sulfuric acid electrolyte, a plastic case, and various contaminants, each requiring its own handling protocol. So batteries are sorted, inspected, and sent to specialized recycling facilities. Essentially, an old battery arrives at the plant as a complex industrial object that can't just be destroyed. It has to be carefully broken down into valuable and hazardous fractions. And here's the main advantage. Battery design has long been known and well standardized, meaning industry knows how to build a highly repeatable, predictable, and economically viable recycling loop around it. The first major phase is mechanical disassembly. At the plant, units are fed into specialized systems where the casing is opened and broken down in a controlled manner. After that, the contents enter a separation stream where sorting by physical properties begins. Plastic components, lead elements, and electrolyte must be routed into different recycling pathways. At this stage, the battery stops being a single product and becomes a set of individual materials. Lead appears as grids, paste, and other internal parts. Plastic, typically polypropylene, is separated out on its own. The electrolyte requires separate treatment because it's a chemically active medium that can't be dumped carelessly. Mechanical disassembly may seem rough, but it's actually highly organized. The goal is to ensure each material goes down its own branch with minimal loss and maximum safety for workers and the environment. After the initial separation, the focus shifts to the electrolyte, the battery's acidic component. This makes recycling not just metallurgical, but chemical too. You can't just dump sulfuric acid solution, so it's either neutralized or converted into other products. Modern facilities tightly regulate this step because ecology, safety, and equipment protection all matter. Meanwhile, solid components continue sorting. Lead parts and pastes move to metallurgical processing, while plastic goes to separate cleaning and prep. Essentially, after this stage, you see how well-suited batteries are for industrial cycling. Very little random material inside, but plenty that can be put back to work. That's exactly why lead-acid batteries are considered one of the best examples of secondary raw materials, where economic incentive and environmental necessity point the same direction. The real value in an old battery is the lead. That's largely why the entire recycling system exists. Once separated from the casing and other components, the lead fractions head to secondary smelting. But this isn't just melting scrap. What matters is restoring metal of the right quality, cleaning out contaminants, converting it into a form ready for manufacturing, and ensuring consistent composition. lead from batteries goes right back into making new ones. That's what makes the cycle nearly closed loop. An old battery becomes raw material for a new one. From an industrial standpoint, this is highly advantageous. Recycled lead cuts virgin mining, reduces dependence on ore, and takes pressure off natural resources. But secondary smelting remains a zone of heightened responsibility because you're dealing with a heavy metal, demanding strict control over emissions, filtration, and worker safety. A closed loop only works when technological discipline is solid. Plastic matters just as much. Most car battery cases are made from polypropylene, which means after proper cleaning, it can be recycled and returned to industrial use. Once separated, the plastic pieces are washed, cleaned of contaminants, and converted into pellets or other secondary material for new manufacturing. So even the battery shell doesn't end up in the trash. It rejoins the recycling loop. This combination of lead, plastic, and controlled electrolyte handling makes battery recycling one of the most efficient operations in the world of secondary materials. This isn't chaotic scrap collection. It's the recycling of a standardized product where every major component has value and a known route back into industry. That's why an old battery is a rare example of a mass-market product, practically destined from the start, not for the landfill, but for a return to production. But high efficiency doesn't cancel out high danger. Recycling car batteries is one of those fields where a mistake can cost dearly, both for people and the planet. There's the risk of acid exposure, heavy metals, dust emissions, and contaminating air, water, and soil if the control system isn't built right. That's why modern facilities must operate with strict filtration, containment, worker protection, and monitoring. Industrial hygiene is especially critical because lead is a cumulative toxic metal. In other words, battery recycling isn't just a profitable scrap business, it's a zone where technological culture determines everything. When a plant is built right, hazardous waste becomes a managed resource. When it's not, recycling itself becomes the source of problems. That's why the best facilities don't build operations around break it down and melt it, but around total control over every material stream inside the plant. That's exactly why lead-acid batteries are held up as a textbook example of an almost perfect circular economy. An incredibly high percentage of the material makes it back into production. The lead returns to new batteries, the polypropylene goes back to manufacturing, the electrolyte gets processed under controlled conditions. Even basic market economics support this loop. An old battery is simply too valuable to throw away. It has a clear buyback price, steady demand from recyclers, and an established industrial system refined over decades for the mass automotive market. That's why battery recycling stands apart. It's economically viable on its own merits, not just because of regulations. It's a rare case where waste is genuinely treated as raw material. What we're looking at is a true closed-loop industrial system.
But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydro turbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydro turbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining. But the foundation of its strength, that's laid right there on the press. 80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys: titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013, China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then the upper plate of the press begins its descent, slowly, almost ceremonially. But behind that calm lies 80,000 tons of force.
Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans. Excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure.
Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing.
China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty.
There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants, still running in defense plants today.
The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.
Every year, the world produces over 1,200,000,000 wool products. Sweaters, scarves, coats, all made from a material that's remained essential in the textile industry for thousands of years. But what makes ordinary sheep's wool so special? Behind every warm sweater lies a process where nature meets cutting-edge technology. From shearing sheep to finished fabric, wool undergoes an incredible transformation. How does a clump of dirty fleece become an $80 billion a year industry? Stick around to the end and you'll discover how an industry turns nature's gift into the foundation of global fashion. The wool industry is a massive machine that processes over 4 billion pounds of wool every year. That's nearly 2 million tons. 3 countries control more than 60% of global production: Australia, China, and New Zealand. Australian farms specialize in fine, high-quality merino wool, which commands the highest prices. China, meanwhile, is the biggest processor and consumer. Thousands of textile factories there transform raw fiber into finished products. The economic value of the entire wool industry tops $80 billion annually, including exports of raw fiber and finished goods. But wool's biggest advantage? It's a completely renewable natural material. Sheep grow new fleece every year, making this one of the most eco-friendly industries in the fashion world. The journey of wool begins on the endless pastures of New Zealand and Australia, where farmers manage their flocks by the strictest standards. Each farm carefully selects sheep breeds based on production goals. Merinos produce ultra-fine fiber for premium clothing, while Romney or Corriedale breeds generate longer, stronger fibers for industrial use. Every sheep gets a personal tag, recording age, health, and wool quality. Flocks graze on rotational plots, preventing soil depletion and preserving the land's fertility. Their diet is supplemented with hay, grain, and minerals to grow dense, uniform, and lustrous wool. Pens stay dry and well ventilated to prevent parasites and skin diseases. Each season, farmers vaccinate, deworm, and inspect every animal because a sheep's health directly determines fiber quality. Before breeding season, sheep undergo a process known as flushing. Their diet gets enriched with special supplements for several weeks to boost fertility and produce stronger lambs with finer fleece. During lambing, mothers are closely monitored so newborns get milk right away. A few weeks later, the young ones are tagged, weighed, and moved to lush pastures for weaning. When the warm months arrive, flocks are washed, treated for ticks, and left to air dry naturally before shearing. Each sheep is handled gently to avoid stress and yield a single clean fleece without tears. After shearing, they're inspected again. Minor cuts are treated, and they're given time to rest before heading back to the fields. Every stage, from nutrition to shearing, follows strict animal welfare standards because only healthy sheep can produce the clean, durable wool of highest value. After months of care, when the sheep's fleece has fully grown back and the weather starts warming up, shearing season arrives. The timing's perfect. Sheep stay comfortable after losing their warm coat, and they've got plenty of time to grow a new one before winter hits. Before the process begins, the flock's kept in clean, dry pens and given lighter feed portions to keep the animals calm. Shearers are highly skilled professionals trained to work safely with each animal. They use precision electric clippers with fine blades, moving in a specific sequence, starting with the belly and legs, then working their way to the sides, shoulders, and back. The goal? Remove the entire fleece in one smooth, continuous motion without damaging the fibers. An experienced shearer can process 200 to 250 sheep in a single day, spending just 1 to 2 minutes on each animal. Short, dirty wool from the belly and legs gets separated for lower quality products, while the long, fine white fleece from the back and sides is reserved for premium fabric production. After shearing, sheep are checked for cuts or scrapes, treated with antiseptic, and sent to rest in wind-protected pens. Each large fleece, the result of an entire year of care and growth, now becomes the very first raw material in wool's industrial journey. From the shearing sheds, fresh fleeces head straight to the sorting zone, where human expertise remains irreplaceable, even amid modern automation. Each fleece gets laid out on wide tables and examined for color, fiber length, and fineness. Any sections tangled with grass, dirt, or too short for spinning get removed. Experienced sorters divide the fleece by zones. Wool from the belly and legs is reserved for industrial use, while the long, clean fibers from the back and sides are set aside for fine fabrics. This meticulous stage not only maximizes the value of each fleece, but also ensures consistency in production batches before the wool is compressed into bales and shipped to the washing plant. Once the sorting process is complete, clean fleeces are collected and moved to the pressing area. Here, powerful hydraulic presses compress each batch into dense rectangular bales, weighing between 300 and 400 pounds, tightly wrapped in burlap or heavy plastic for moisture protection. Each bale is marked with detailed information, including the farm of origin, sheep breed, and wool grade, ensuring full traceability throughout the supply chain. At the raw material processing plant, the wool bales are unpacked and evenly distributed onto conveyor belts for cleaning. The first stage happens inside an opener, a machine equipped with several rows of high-speed rotating metal teeth, designed to separate tangled fibers and remove trapped contaminants like dust, grass, and dirt. This loosens the wool and prepares it to better absorb water in the next washing stage. The washing system consists of 6 continuous tanks of hot water, operating at temperatures between 168 and 180 degrees Fahrenheit. The first 3 contain diluted soapy solution to dissolve lanolin, the natural oil secreted by sheep that protects their fleece from moisture. The remaining 3 are filled with clean water for thorough rinsing. Water is filtered and circulated in counterflow through automatic pumps, conserving energy and maintaining consistent quality across all batches. Between each tank, soft press rollers gently squeeze out dirty water without damaging the fibers. Temperature and flow sensors automatically adjust washing parameters to keep the system at optimal safe levels. The extracted lanolin is collected and refined separately for use in cosmetics and pharmaceuticals. Finally, the clean wool enters a rotary drum dryer, where warm air circulates evenly as the drums continuously rotate, allowing heat to penetrate every strand. When the process is complete, the fibers reach a standard moisture level of around 12%, soft, vibrant, and completely free of contaminants, ready for storage and quality control. The dried wool bales are fed into a fiber blending machine. Each batch, varying in color, fineness, or origin, is precisely weighed and blended by rotating rollers with spiral blades that separate fibers clumped together during drying. A spray system maintains air humidity and prevents static, while sensors monitor speed for perfect uniformity. The fibers emerge soft, light, and springy, ready for the next mechanical stage. Entering the structural formation phase, the dried wool is fed into the carding section, where loose fibers are aligned in a single uniform direction. The material passes through a carding machine equipped with multiple metal-toothed rollers rotating at different speeds to create controlled friction and pulling force. Through this continuous motion, tangled fibers separate, straighten, and gradually clean themselves. Throughout the entire process, dust removal systems and electronic sensors eliminate short fibers, fine dust, and contaminants left over from previous cleaning stages. When the material exits the chamber, it emerges as a thin, continuous web of fibers, which automatically coils into soft slivers of consistent thickness and weight. After the carding stage is complete, the long and cleaned wool slivers move to the spinning section, a critical phase that determines the strength and fineness of the material. Here, the fibers enter a multi-roller spinning frame, where each roller spins at slightly different speeds to apply gradual drafting tension. The front rollers hold the fiber steady, while the back rollers accelerate slightly, drawing the sliver thinner while maintaining its elasticity and internal cohesion. Before the twisting unit, the surface of each strand is coated with an ultra-thin layer of spinning oil, reducing friction and preventing static buildup. As the fibers pass through the central twisting unit, they bind tightly together into a single strand, forming a structure that's both strong and elastic. The degree of twist is controlled by tension sensors, ensuring perfect consistency along the entire length of the yarn. The finished threads are wound onto large spools, then rewound into smaller, standard-size bobbins. Optical scanners inspect every strand in real time, detecting thick spots, weak points, or over-twisted sections. Any defects are automatically cut and joined using thermal welding, creating smooth, seamless connections almost invisible to the naked eye. In the next stage of production, the wool threads, now refined to the perfect balance of fineness and strength, enter the weaving system, where the material transforms from loose threads into a unified textile structure. And just like that, having traveled from vast pastures through washing, carding, spinning, and weaving, ordinary sheep's wool becomes the foundation for warm sweaters, elegant coats, and luxurious blankets that keep millions of people around the world cozy.
Every year, humanity throws away more than 50 billion batteries. That's enough to build a tower all the way to the moon. Mountains of toxic metal and chemicals that could become raw material for new life instead of poisoning the planet. But what happens next to all these power sources? Where do they end up after the charge dies in your phone, laptop, or electric car? Behind the plain doors of an ordinary collection point hides an entire industry of the future. This is a world of giant shredders that grind metal into dust, magnetic separators that sort the invisible, and furnaces reaching temperatures of 3,000 degrees Fahrenheit, hotter than the mouth of a volcano. And here's the best part. By the end of this video, you'll find out what actually happens to the lithium that once lived inside your battery, and why this process is called urban mining for 21st century treasures.
The path to rebirth doesn't start at the factory, it starts in our hands. Collecting used batteries is a massive logistical operation spanning the entire country. Regular people drop off tiny batteries from phones and laptops into special bins installed at electronics stores and supermarkets. Auto shops, like hospitals for cars, pull out massive battery packs from electric vehicles, hundreds of pounds each. Industrial facilities running heavy machinery turn in their spent power sources by the ton. It's like thousands of streams flowing into one big river. Old batteries from factories and auto shops get hauled in armored trucks to regional collection centers. Here's what's interesting. Modern smart collection containers have sensors that track fill levels in real time. When a container's almost full, it automatically sends a signal to the logistics company, which plans a pickup route. When mountains of collected batteries arrive at the sorting facility, one of the most complex and critical stages begins. Batteries come in dozens of different types. Lithium-ion, like the one in your smartphone, nickel metal hydride from old toys, lead acid from cars. Mixing them during recycling is like mixing sand with sugar. At small collection centers, workers sort batteries by hand, like jewelers, relying on markings and appearance. But at large-scale facilities, technology takes over. Batteries move along conveyor belts under the watch of artificial intelligence. Computer vision systems equipped with X-ray and spectroscopic scanners identify the chemical composition of each battery in fractions of a second. Robotic arms snatch the right types from the stream at lightning speed and sort them into different containers.
Despite automation, human oversight remains irreplaceable. Operators, like air traffic controllers, monitor the machines and step in when things get complicated. If a battery has a damaged casing or missing labels, only a human can make the right call. This is especially true for the massive batteries from electric vehicles. These giant blocks, weighing up to half a ton, are dismantled into smaller modules using specialized robots, but the final cell sorting is often done by hand. It's painstaking and dangerous work that demands total focus. At the end of the day, every properly sorted battery isn't just a piece of metal. It's a chance to return the most valuable rare earth elements, like cobalt and lithium, back into the economy, and to reduce the enormous damage caused by mining them in the first place.
After sorting, the batteries head to their execution, the shredding floor. They fall into the steel jaws of a giant shredder. This is a true industrial monster, whose hardened steel blades can grind up even the armored casing of an electric vehicle battery. Inside the protected chamber, total metallic chaos unfolds. Deafening roars, grinding, and cracking. Batteries literally torn into tiny pieces. But this process is extremely dangerous. Any energy left in a battery can lead to fire or explosion. To prevent this, engineers developed several brilliant solutions. Before shredding, batteries are often subjected to cryogenic freezing in liquid nitrogen at temperatures of -320 degrees Fahrenheit. This not only makes the metals more brittle, but also completely neutralizes any chemical activity. Some shredders operate in sealed chambers filled with inert gases to eliminate contact with oxygen. The shredded pieces pass through a system of magnetic separators that pull steel, nickel, and cobalt from the stream with incredible precision. But the most valuable thing is the fine black powder that settles in specialized dust collectors. It's known as black mass. Right here in this unremarkable-looking dust lie the real treasures of the 21st century: lithium, cobalt, manganese, and graphite. Plastic residue and traces of electrolytes get washed away with special solutions. Engineers in armored control rooms monitor the process through thick glass, controlling temperature and pressure. If a battery does explode, the system instantly snuffs out the flash, and the process doesn't stop for a second.
Once the precious black mass has been extracted from the chaos of shredded batteries, the real alchemy begins. Metals that seemed forever locked inside old batteries are recovered using two main methods, hydrometallurgy and pyrometallurgy. Hydrometallurgy is a process similar to cooking up a complex chemical soup. The black mass is plunged into massive reactors filled with acid solutions, typically sulfuric or hydrochloric acid. With constant stirring and heating, metals, lithium, cobalt, nickel, literally dissolve, transitioning into liquid form. To extract a specific metal from this soup, an ion extraction process is used. Special reagents are added to the solution that selectively bind to only one metal, like a key to a lock. As a result, each metal settles into a separate layer. If hydrometallurgy is delicate chemistry, then pyrometallurgy is the primal force of fire. Here, everything literally burns and melts. The black mass gets loaded into a massive arc furnace, where temperatures reach nearly 3,000 degrees Fahrenheit. At that kind of heat, metals melt, and plastic and other organic remnants simply burn away. The molten mass separates under gravity, like oil and water. Heavier metals, such as cobalt, nickel, and copper, sink to the bottom, forming a valuable alloy. The lighter lithium stays in the top layer, in what's called slag. Then this slag is extracted and processed separately to obtain pure lithium. This method is faster and handles larger volumes, but it's also more energy intensive. After cooling, the extracted metals emerge as the purest ingots, shiny, smooth, and ready for their second life. Cooling after the pyrometallurgical process is just as critical a stage. If you simply let molten metals cool in open air, it can take several days and lead to uneven crystal structure formation, which degrades quality. That's why cooling is always controlled. Ingots might move slowly along a conveyor beneath powerful fans. It's like a giant hairdryer that quickly yet evenly cools the surface. For an even faster process, red-hot ingots can be plunged into massive tanks of water or special cooling fluids. It's an incredible sight, glowing metal hitting water instantly shrouded in clouds of hissing steam.
Sometimes they use combined cooling too, air cooling first, then water cooling, to reduce internal stress in the metal. Controlled cooling ensures a uniform metal structure, which is critical for reuse, especially in manufacturing new high-tech batteries. The recovered lithium, now in the form of ultra-pure lithium carbonate, heads back to factories to become the heart of new batteries that'll power electric cars or even your phones. Nickel can become part of super strong alloys for turbines that generate energy from wind, and cobalt becomes an irreplaceable component in complex medical equipment. We're literally closing the loop. Old, discarded batteries give life to new, cutting-edge technologies.
Tossed batteries, they can become a full-blown environmental disaster. First, they're packed with toxic heavy metals that seep into landfills, contaminate soil, poison groundwater, and wreck everything around them. Second, mining new rare earth metals is an incredibly dirty, destructive process that drains natural resources and devastates ecosystems on a massive scale. Recycling tackles both problems at once. And here's the real power move. The more batteries we recycle, the less we depend on unstable raw material supplies from other countries, strengthening our technological independence. Despite lithium's critical importance, only about 1% of this metal gets recycled globally today. The main reason? High costs and complex processes. But right now, researchers around the world are developing new, cheaper technologies that could dramatically change the game in the coming years.
Hey everyone, on this channel we go behind the scenes where cameras usually aren't allowed. If you're into this kind of breakdown, hit subscribe and tap that bell so you don't miss new episodes. Every year, the world recycles over 1.5 billion tons of scrap metal, and hidden within this chaos of rust and mangled iron is something way more valuable than it looks. What seems like trash today could save your life tomorrow at 75 miles per hour. But how exactly does this pile of metal transform into a precision-engineered component trusted by millions of drivers? And why can even a tiny 1% error destroy an entire batch? There's one detail in this process almost nobody talks about, and it's what determines whether your car stops when it really matters. Today, we're breaking down the entire production of brake rotors, from the furnace to final inspection. It all starts with what most people would just call a junkyard. And that's pretty ironic. What will later stop your car at 75 miles per hour, right now looks like a giant pile of rusty junk. Old cast iron radiators, car body fragments, twisted beams, and other metal scrap. It's all stacked in heaps on the lot outside the plant, and rain sends rusty orange streaks running down into the asphalt. But to this factory, it's all treasure. A massive electromagnet hanging from a crane scoops up several tons of this iron and drops it with a crash into the throat of a giant induction furnace. Induction, meaning the metal doesn't melt from fire, but from an electromagnetic field that heats it from the inside out, evenly and fast. If you stand too close, it's kind of terrifying. The furnace hums at such a low frequency that you don't really hear the sound. You feel it deep in your chest, like your heart's trying to sync up with this heavy industrial rhythm. The temperature inside the furnace climbs to 2,700 degrees Fahrenheit. At that kind of heat, even the toughest steel turns into liquid, more like glowing, ridiculously dangerous soup than anything solid or dependable. When the furnace tilts to pour out the molten metal, everything around you floods with bright orange light that makes you want to squint. No artificial beauty here, just brutal physics and an insane amount of heat. Every batch of metal gets tested instantly. Lab techs in special suits grab a small sample, cool it down, and within seconds determine its chemical makeup using a spectrometer. The device breaks the sample down into elements and spits out precise percentages of each component. If the carbon or silicon content deviates from spec by even 1%, the entire massive batch gets sent back for remelting without hesitation. Mistakes aren't tolerated here, because the cost of that kind of error to the end user could be way too high. Next, they pour this liquid fire into molds. They use sand casting technology here. Sand seems like an unreliable material, but at this factory, they mix it with special resins and under enormous pressure, it becomes hard as concrete. The molds are made with jeweler-like precision. The internal relief copies every detail of the future disc, including cooling fins and mounting holes. Metal fills the cavities inside the sand mold, and it's at this exact moment that the rough blank of the future brake disc is born. It doesn't look anything like that shiny part we're used to seeing in auto parts stores yet. Instead, it's something big, heavy, and really dirty. After pouring, the discs need to cool naturally. It's a long process, sometimes taking several hours, and this is critically important. If you try to speed up the cooling, say by splashing water on it, the metal becomes too brittle. A disc like that could just shatter into pieces at the first hard stomp on the brake pedal somewhere out on the highway in the rain. When the blanks cool down to just warm instead of glowing red hot, they head to the machining shop. This is where robot territory begins. They work 24/7, no lunch breaks, no complaints about tough working conditions. Each disc gets grabbed by a manipulator arm that loads it into a CNC machine. Special cutting tools shave off excess metal as easily as if it weren't solid cast iron, but a stick of cold butter. Chips spiral out red hot and drop into a collection tray while a smooth, precisely calibrated surface emerges from under the cutter. At this stage, fanatical precision rules. A deviation of 0.8 of a millimeter means hopeless scrap. A disc like that never makes it to the warehouse because it'll cause vibration that'll just destroy a car's suspension in a few months and force the driver to shell out a ton of cash for repairs. The machine finishes one disc in several minutes, and each one comes out identical to the last. Robots don't get tired and don't lose focus by end of shift. It's fascinating to watch as the perfect, almost mirror-like surface gradually emerges from a rough and ugly form. Then they drill ventilation holes and internal channels into the discs. This isn't done for visual style like some people think. It's a critically necessary cooling system, without which the discs simply wouldn't survive serious loads. During heavy braking, the disc can heat up to 1,300 degrees Fahrenheit. At that temperature, it glows dark cherry red. If this heat isn't removed in time, the metal starts losing its friction properties, and the brakes just disappear at exactly the wrong moment. So these holes and channels, they're the result of extensive engineering calculations, not some design decision for looks. Each channel has a precisely determined diameter and angle, calculated so airflow pulls heat away from the working surface as efficiently as possible. Once all the excess shavings are removed, each rotor gets sent to dynamic balancing. It's a lot like what they do to your wheels at the tire shop, but the precision here is tens of times higher. A special device spins the rotor up to enormous speed and uses sensors to detect the slightest weight imbalance. At these rotational speeds, any imbalance turns into noticeable vibration, and the machine picks it up with gram-level accuracy. If one side turns out to be heavier by even 3 or 4 grams, the machine automatically drills out a tiny, nearly invisible dimple in just the right spot on the face to even out the weight. After that, the rotor is perfectly balanced and ready to perform at any RPM without any extra noise or judder. It's at this stage that the difference is made, whether the driver will feel every imperfection through the pedal or whether braking will stay smooth and silent at any speed. I asked the chief engineer how many of these rotors they produce in a single full workday. He just smiled wearily and said they stopped counting them individually a long time ago. They track output in thousands of tons of finished product per month. Just think about that for a second. This facility supplies parts for nearly half the European automotive market, which means every other car you see on city streets is probably stopping with rotors made right here, in this loud, scorching hot plant. Before packaging, the rotors go through a protective coating process. They're either painted with a special heat-resistant paint or coated with a thin, anti-corrosion, zinc-based layer. The coating gets applied in a chamber, the rotor hangs from a conveyor, and automatic sprayers evenly cover it from all sides. This is done so they don't turn into a rusty chunk of metal during long-term warehouse storage or while crossing the ocean in a shipping container. Sure, after the first few miles of driving, this paint on the working surface will completely wear off under the massive friction from the brake pads, but the edges and internal parts will stay protected from road salt and grime. The final, and arguably most critical stage, is the quality control check. And we're not talking about some tired worker giving it a quick once-over at the end of their shift. They use ultrasonic scanners and X-ray machines. They're hunting for internal defects, air bubbles or micro cracks you couldn't spot even with a magnifying glass. Ultrasound sends a wave through the metal, and if there's a void inside, the signal bounces back distorted. The machine flags the problem zone instantly. Even if the disc looks flawless on the outside, but the X-ray reveals a cavity just 2 millimeters wide somewhere deep in the metal, it gets sent straight to the shredder. Nobody cuts corners on safety here, because everyone knows full well, this part directly determines whether the driver and passengers live or die.
Each year, humanity produces over 400 million tons of plastic, of which 23 million tons end up in the oceans, forming gigantic rubbish islands the size of entire countries. Consider the Great Pacific Garbage Patch alone, which covers an area 3 times that of France. Just imagine, this isn't merely rubbish, but a threat that kills millions of marine creatures annually. And by the year 2060, the oceans will be drowning in 141 million tons of plastic. But would you believe that this blot doesn't actually exist in the form we imagine it? It's an invisible trap concealing a secret. How an ordinary teenager invented a method to clean the oceans without engines, using only the forces of nature? And if you watch to the end, you'll discover revolutionary robots sorting rubbish faster than lightning, and the Interceptor, which blocks plastic in rivers using solar power, a secret that will forever change your perception of the planet's future. The waste management sector is undergoing a technological revolution, thanks to the introduction of artificial intelligence and robotics. At modern waste processing facilities, robotic arms controlled by sophisticated algorithms sort refuse at remarkable speed and with exceptional precision. Computer vision systems identify different types of materials, enabling a significant increase in recycling rates. Along a wide conveyor belt moves a continuous, chaotic stream of what we've discarded: plastic bottles, crushed cardboard boxes, aluminum cans. To the human eye, it's simply rubbish, whilst for workers it represents arduous and hazardous labor. And there, above this flow, rather like a relentless predator, it hovers: the sorting robot. This isn't a humanoid android from science fiction films, but rather a high-tech industrial manipulator resembling a giant steel arm. Yet all its magic lies within. Its eyes aren't merely cameras, but complex multispectral sensors that perceive the world quite differently from us. They can distinguish materials by how they reflect light and analyze their chemical structure in fractions of a second. The heart and brain of the system is artificial intelligence. Before being deployed on the job, this AI underwent intensive training. It was shown millions of images of various types of waste until it learned to recognize them flawlessly. In this way, the robot learned to identify PET plastic, from which drinks bottles are made, denser plastic for canisters, paper, cardboard, various types of metals, and glass. And so the action begins. The conveyor belt races onwards. The camera scans the flow continuously. Artificial intelligence analyzes the image in real time. Target identified, aluminum can, it sends the signal. And a steel manipulator makes a lightning-fast, almost imperceptible lunge. A pneumatic suction cup or mechanical gripper gently but firmly seizes the can, and with a precise movement, drops it into the appropriate container. Before the can has even landed, the robot's eye has already spotted a water bottle, and the arm flies towards the new target once more. Speed? A human cannot compare with it. Some models are capable of making 100 manipulations per minute. That's more than 1 grab per second. Accuracy? The robot doesn't tire and doesn't get distracted. Its sorting efficiency reaches more than 95%, which significantly improves the quality of recyclables. This isn't simply a replacement for manual labor. It's a qualitative leap, which transforms the problem of rubbish into a genuine resource. The sorted materials, heaps of rigid plastic, cumbersome metal structures, wooden pallets, lie in separate mountains. They've already been sorted, but they're still far too large. It's here that the real heavyweight of the recycling industry enters the arena, a machine whose work is controlled, brutal force. This is the hammer mill. Outwardly, it resembles an enormous steel box, but its heart is a massive, heavy rotor, studded with rows of exceptionally robust, hardened steel teeth or hammers. Its task is simple, yet critically important: to shred. When material is fed into its vast maw via conveyor,
Be it an old car bumper or an entire pile of plastic drums, a spectacle of unstoppable power begins. As it rotates, the rotor's teeth seize hold of objects, dragging them inwards, and with a deafening roar and grinding, tears them to pieces. Rigid plastic cracks, metal bends and rips, wood transforms into splinters. This process is a demonstration of pure physical force. But what purpose does this destruction serve? It isn't senseless obliteration, but rather a crucial preparatory stage. Firstly, the shredded materials become uniform in size, which makes them far more convenient for transport and subsequent processing. Secondly, it's a process of liberation. The shredder breaks down complex objects into simpler components, facilitating the separation of different materials from one another. And most importantly, it creates ideal feedstock for further recycling. A heap of small plastic fragments melts far more readily in a granulator than intact bumpers. Vast accumulations of plastic in the world's oceans, such as the Great Pacific Garbage Patch, represent one of the most pressing environmental concerns. Incidentally, do you believe this patch doesn't exist? Nevertheless, through bold engineering solutions, hope emerges for cleansing our marine spaces. The problem is so enormous it appears insoluble. How does one remove something the size of several countries? Most simply threw up their hands, but not Dutch teenager Boyan Slat. In his mind was born a daring yet brilliantly simple idea, which grew into one of the most ambitious environmental projects of our time, the ocean cleanup. The project's principle is not to chase the plastic, but rather to make the ocean itself deliver the rubbish into the trap. For this purpose, giant U-shaped barriers were created. The most intriguing aspect is how this system moves. It has no engines. It drifts passively, caught by the same forces that carry the plastic: wind, waves, and ocean currents. But owing to its design, the system moves slightly faster than the plastic. This creates a small but constant difference in speed. The barrier, rather like a giant shepherd, slowly but inexorably gathers its plastic flock within its U-shaped arc. The path to success wasn't straightforward. Early prototypes fractured under the onslaught of ocean storms, but after a series of trials and errors, the system began working effectively. Now, from time to time, specialized vessels approach the laden barrier and offload the collected tons of plastic. This plastic, from old fishing nets to minute fragments, is brought ashore, where it's sorted and sent for recycling, closing the loop. Realizing that cleaning the ocean without stopping the flow of rubbish is rather like bailing water from a leaking boat, the ocean cleanup team asked themselves a logical question: couldn't one simply plug the leak? After all, research shows that the overwhelming majority of plastic enters the ocean through only a small number of the world's most polluted rivers. Thus was born the Interceptor, a technology designed to tackle the problem at its source. It resembles an elegant, futuristic catamaran, anchored mid-river. It is entirely autonomous and runs 100% on solar power, courtesy of the panels covering its upper portion. Its design has been thought through to the smallest detail, so as to be maximally effective whilst not interfering with shipping.
Every hour across the globe, dozens of nuclear reactions, but only a handful know that at the heart of every atomic bomb lies a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, crafted by human hands. You'll discover how ordinary uranium births an explosion with the force of 1,000 suns, why sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret hides inside a nuclear warhead? Watch until the end, because the finale will change how you see the modern world.
Back in the day, when the world was just learning to hear the voice of the atom, a few curious minds peered inside the invisible, into the heart of matter. Those were the years when science was feeling its way forward, but with great determination. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered that uranium could split. It was as if ice cracked on a river, behind which a giant lay sleeping. While Europe prepared for war, a group of people secretly gathered across the ocean, later to be called the Masters of Atomic Fire. In the New Mexico desert, the Manhattan Project began. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, beneath the clouds of dawn, the first nuclear bomb exploded. Sand turned to glass, sky to fire. And in the absolute silence, one scientist whispered, "Now I am become death, the destroyer of worlds."
But the story didn't end there. Days later, Hiroshima and Nagasaki became pages of grief. And just when the world thought it had seen everything, the USSR answered. Under Igor Kurchatov's leadership in 1949, the first Soviet atomic bomb detonated. A decade later, the Tsar Bomba. Its power could level a city the size of Paris. History's irony. Nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. Ideas of security, control, diplomacy became more important than warfare. For the first time, humanity faced massive questions. Can we negotiate so everyone survives? That's how deterrence doctrine was born. Don't attack, because you know attacking means catastrophe. And while this balance is far from perfect, it's delivered decades without global war between superpowers. An entire era. Cold, anxious, but without mass battlefronts.
Nuclear research sparked whole new industries: nuclear power, reactors on submarines, medical diagnostics. Even space projects got a boost from understanding the atom. To create the most terrifying thing, we learned to grasp the most complex. Yes, nuclear weapons are dangerous, but they're also a mirror of human wisdom. We built something incredibly powerful and chose not to use it on a massive scale. This is a story about power we decided to restrain, about science that taught us not to dominate, but to coexist. Deep in laboratories, where lamplight dimly illuminates blueprints, the path to building a nuclear bomb begins. This isn't just assembling metal, it's modern-day alchemy, where every gram of material holds the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction.
But natural uranium is mostly uranium-238, which won't work, so they enrich it, separating out the 235 isotope using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It's produced in nuclear reactors, where uranium absorbs neutrons and transforms into plutonium, the stuff you need for a nuclear bomb. The appearance of a nuclear bomb often resembles a classic aircraft bomb, a streamlined metal casing engineered for stable descent from high altitude. In a massive hangar where the walls ring with the echo of metal, the air smells of hot steel and oil. Here begins the birth of the shell that must contain the heart of an atomic explosion. From the glowing throat of an industrial furnace flows a stream of metal, special steel, reinforced with nickel, chromium, and manganese. Its temperature exceeds 1,000 degrees. Summer sunlight looks pale compared to this fire.
Masters in protective suits with transparent face shields watch the forming process. Steel sheets bend into streamlined shapes under presses exerting hundreds of tons of force. Before their eyes, an elongated body takes shape, resembling a water droplet frozen under the pressure of the heavens. Next, mechanical arms mill the internal partitions, cut openings for tail stabilizers and locking mechanisms. Every fraction of an inch, the result of meticulous calculation, because balance during descent depends on it. After this, the casing undergoes a strengthening ritual: immersion in an anti-corrosion bath, treatment with polymer coating, application of matte paint. The color? Dark green, like a military shadow in the twilight of pine trees. And finally, testing. They drop it from height, strike it with hammers, spin it in a wind tunnel. Only after passing all trials is the casing ready to receive its lethal payload.
A quiet lab, half light, a faint smell of ozone, something heavy hangs in the air. In front of you lies an open nuclear bomb, its metal casing removed, its insides, like an organism, laid bare. There's nothing extra here, no shine, no decoration, just function, just explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear core. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in your palm. Its shape, mathematical perfection, polished down to microns. Around the sphere, an entire symphony of pressure. Composite explosives, layer upon layer, like a flower turned inside out. Their job isn't simply to detonate, but to force the explosion inward. Like hands clenching to the limit, these explosive lenses must create implosion, uniform, merciless compression that drives the material supercritical.
If even 1 second lags, the whole contraption becomes a heap of meaningless metal. And at the very heart of this implosion orchestra, the initiator, a tiny device waiting for its moment to release the first neutrons. Polonium and beryllium interact, creating a minuscule storm capable of triggering the irreversible. That's where the chain reaction begins, a match to an atomic forest. Then, the tamper layer. Heavy as a shadow, it wraps the bomb's core not for protection, but for containment. Uranium-238 or tungsten, not active, but absolutely critical. Their job? Delay the neutrons, force them back like an echo in a cave. Everything depends on this. The duration of the blast, its power, its climax. In the tail section, the brain. Automation, electronics, wires and sensors. Barometers waiting for altitude, radars tracking the ground, batteries sleeping, ready to wake.
This is where it's all decided, when everything happens, above the city, in the air, after the drop. Without this nervous system, the blast would be an accident. But here, it's a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, like chapters in an encyclopedia of force. The outer shell, smooth and cold. The explosive layer, mathematically arranged. The tamper, an invisible guardian. The core, like a seed of what's to come. And at the very center, a spark, sleeping until awakened. Over 62 years, the world witnessed 2,065 nuclear explosions. 5,224, that's not the number of nuclear explosions, but an approximate estimate of the entire U.S. arsenal, including active, reserve, and decommissioned warheads. Now, the number of nuclear tests that the United States conducted from 1945 to 1992 totals 1,154 detonations.
Each one is a separate page in the history of power, fear, and science. The first blast, Trinity, July 16, 1945, in the New Mexico desert. It was the beginning of an era when atomic energy became a weapon. Then came Hiroshima and Nagasaki, the only instances of nuclear weapons used in combat. In the decades that followed, the U.S. tested bombs at Enuatak and Bikini atolls, in Nevada, underground, in the atmosphere, over water. The blasts had different purposes: testing new designs, demonstrating power, studying effects on equipment and living organisms. Yield varied, from a few kilotons to 15 megatons, like in the Castle Bravo test of 1954. In 1952, the US conducted its first thermonuclear test, Ivy Mike. This wasn't just a bomb anymore, but a miniature star created by humans. The explosion wiped out an entire island.
In the 1960s, testing became routine. The US tested warheads for missiles, aerial bombs, even neutron charges that had minimal blast waves but maximum radiation. The last official detonation happened on September 23, 1992, after which the US declared a moratorium, but the arsenal remained. It gets modernized, adapted, stored. Some warheads are on submarines, some on strategic bombers, some in NATO storage facilities. These explosions aren't just technical events. This is a story about how humanity learned to control the energy of stars and put it in the service of fear. But it's also a reminder that the power capable of destroying civilization sits under the control of those who understand the price of using it. And as long as this balance holds, the world continues to exist on the edge of the abyss, but doesn't fall in.
The 12.7 by 108 mm round punches through 0.8 of an inch steel armor from over half a mile away. Muzzle velocity, 2,800 feet per second. Muzzle energy, 13,000 foot-pounds. That's 30 times more than a standard rifle round. One cartridge weighs 4.5 ounces. Length, nearly 6 inches. But how do you manufacture this in a country under sanctions, cut off from Western technology? Today you'll see the complete production cycle of large-caliber ammunition in Iranian factories, from copper sheet to a round that flies faster than sound. If you want to see how a defense industry operates under isolation, hit subscribe. Here we show you manufacturing facilities nobody talks about. Iran's been making ammunition since the 1940s. After the 1979 revolution and the war with Iraq, the country got hit with sanctions. Western suppliers pulled out. They had to build everything themselves. The Defense Industries Organization, DIO, runs 20 factories. The AMIG Ammunition Production Group cranks out calibers from 5.56 mm all the way up to 152 mm. The 12.7 by 108 mm caliber? That's Soviet standard. Think of it as the Russian equivalent of the 50 BMG. It's used in heavy machine guns like the DSHK and NSV, in anti-material rifles, in anti-aircraft guns. The factory sits in the mountains about 30 miles from Tehran. 50 acres, 1,200 workers. Production runs 24/7, 3 8-hour shifts. They pump out 150,000 rounds a day. That's 55 million a year. The casing is made from brass. Brass is an alloy of copper and zinc. Copper content, 70%. Grade, L70. Brass is ductile. Stamps well, doesn't rust. Supplied in sheets 0.08 inches thick. Sheet size, 3.3 feet by 6.6 feet. Weight, 75 pounds. The sheet is cut into circular blanks 2.75 inches in diameter. A 200-ton press. Guillotine blade. One sheet yields 400 blanks. The blank is stamped on a drawing press. The punch drives into the center. The metal stretches into a cup. Cup diameter, 1.1 inches. Height, 1.18 inches. Wall thickness, 0.06 inches. Force, 50 tons. The cup goes through 7 drawing stages. After the 7th, diameter 0.62 inches, height 4.25 inches, wall thickness 0.04 inches. The base is thicker, 0.12 inches. In the center, they drill a primer pocket 0.25 inches in diameter. Depth, 0.24 inches. On the outside near the base, an extractor groove. Width, 0.12 inches. Depth, 0.03 inches. After stamping, the brass is work-hardened. Tough and brittle, it needs annealing. The cases get loaded into a conveyor-type furnace. Temperature, 1,000 to 22 degrees Fahrenheit. 20 minutes, the brass softens. Stresses release. Air-cooled. Then they're sized through a ring with an internal diameter of 0.62 inches. Tolerance plus or minus 0.0008. The neck gets crimped into a 4-degree taper for a tight bullet fit. Cases are washed in alkaline solution, 3% concentration. Temperature, 140 degrees. 5 minutes. Strips off the oil. Dried with hot air at 212 degrees for 3 minutes. The bullet's made from lead and steel. Steel core, grade 70 steel. Hardness, 220 Brinell. A rod, 0.35 inches in diameter, gets cut into blanks 1.38 inches long, machined on an automatic lathe. Shape, cylinder with a tapered nose. Length, 1.3 inches. Diameter, 0.346 inches. Weight, 0.67 ounces. The casing is made from tombac. Tombac is brass with high copper content, 90% copper, 10% zinc, harder than regular brass. Tombac comes in strips 0.035 inches thick. Stamped on a press, creates a cup half an inch in diameter, 0.8 inches tall. Drawn in 3 stages. Final specs: diameter half an inch, length 2.5 inches, wall thickness 0.028 inches. A steel core goes inside. The space gets filled with lead. Lead melts at 630 degrees Fahrenheit. The casing with the core goes into a mold. Pour. Lead solidifies in 3 seconds. Automated. Output 2,000 bullets per hour. Finished bullet. Length 2.5 inches, diameter half an inch, weight 1.7 ounces. Shape, pointed nose with boat tail. Ballistic coefficient, 0.55. Range, up to 2 miles. They use SNP powder, spherical nitroglycerin type. Base, nitrocellulose and nitroglycerin. 50-50 ratio. Stabilizers, diphenylamine, 2%. Plasticizers, dioctyl phthalate, 3%. Powder comes as spheres, diameter 0.047 inches. Density, 100 pounds per cubic foot. Heat of combustion, 4,000 joules per gram. Burn rate, 0.79 inches per second at 43,500 psi. The charge is dispensed automatically. Weight, 0.46 ounces. Accuracy, plus or minus 0.02 ounces. Poured into the case through a funnel. Primer pressed into the primer pocket. Brass cap, diameter 0.25 inches, height 0.2 inches. Inside, percussion compound. Mercury fulminate 30%, potassium chlorate 40, antimony sulfide 20, ground glass 10. Compound weight 0.003 ounces. Pressed with 330 pounds of force. Seating depth 0.004 inches below the case head. If the primer sticks out, it could detonate during feeding. The bullet gets inserted into the case mouth. Fit is tight. Force 110 pounds. Depth half an inch. The neck gets crimped using a roller. 3 ring grooves hold the bullet in place. Red shellac-based lacquer gets applied to the neck. Seals the joint,
protects the powder from moisture. The primer gets sealed too. A drop of lacquer around the edge. Rounds complete. Length, 5.8 inches. Bullet diameter, 0.50. Case diameter, 0.62. Weight, 4.4 ounces. Bullet weight, 1.7 ounces. Powder weight, 0.46 ounces. Muzzle velocity, 2,800 feet per second. Muzzle energy, 12,700 foot-pounds. Maximum chamber pressure, 52,000 psi. That's 3,600 atmospheres. Every batch gets checked. Each batch is 10,000 rounds. They pull 10 at random. Fire them from a test barrel in a concrete bunker. Walls 3 feet thick. They measure bullet velocity with an optical chronograph. 2 frames spaced 3 feet apart. Bullet crosses the first. Timer starts. Crosses the second. Stops. Computer calculates velocity. Standards 2,700 to 2,800 feet per second. Spread no more than 30 feet per second. They check grouping. 10 rounds at a target from 300 feet. Maximum spread 6 inches. Average deviation 2. They check penetration. Targets a steel plate 3/4 of an inch thick. Range 1,000 feet. Bullet has to punch straight through. If even one of the 10 fails, the whole batch gets rejected. 10,000 rounds go to reprocessing. Casings get melted down. Bullets too. Powder gets burned. Cartridges that pass inspection get packaged. 100 rounds in a wooden crate, 20 by 12 by 8 inches. Weight, 33 pounds. 5 rows of 20. Cardboard dividers between rows. The crate gets nailed shut. Marked with paint. Caliber, quantity, date, batch number. Shipped to warehouses. Underground bunkers in the mountains. Depth, 160 feet. Temperature held constant at 59 degrees. Humidity at 60%. Storage life, 10 years. Then testing. Passed the test. Extended another 5. The 12.7 by 108 mm round is used in the DSHK heavy machine gun. Rate of fire, 600 rounds per minute. Effective range, nearly a mile. Maximum range, almost 2 miles. Penetrates body armor at over half a mile. Punches through a 12-inch brick wall. Stops unarmored vehicles. Destroys radar and optics on armored vehicles. Iran produces these by the millions. Exports them to allies. Without access to Western technology, the country built a complete production cycle, from copper to combat round. This is how ammunition gets made under sanctions. If you found this interesting, hit that like button. Comment below if you knew about Iran's defense industry. Subscribe. We show you what others won't talk about.
Every year, millions of tons of steel get recycled worldwide, but only a tiny fraction becomes tools capable of handling hundreds of tons of force. Picture this: a chunk of metal weighing several tons heated to 2,200 degrees Fahrenheit, hot enough that steel practically flows, and over the course of a few weeks transformed into a giant wrench longer than 10 feet. But there's one detail almost nobody talks about: the slightest mistake at any stage, and this beast can crack under load. Today, I'm showing you a process hidden from most people's eyes, and if you stick around till the end, you'll find out why these wrenches sometimes fail at the most unexpected moment. I step onto the grounds of the steel mill and immediately realize this is where things happen on a massive scale. All around me, the roar of heavy overhead cranes, the smell of hot steel, and the pounding of hammers you can feel in your chest. The master blacksmith greets me, a tall man, hands scarred from past projects, eyes tracking every movement. He shows me a massive billet, a chunk of chromoly steel over 10 feet long, nearly 2 feet thick, and weighing several tons. Chromoly steel isn't chosen by accident. Chromium gives it corrosion resistance, while molybdenum boosts strength under high heat and stress. This massive piece will become the core of the wrench, and it's already impressive on its own. Even from 3 feet away, you can feel its weight, its scale, its raw potential. The process starts with heat. The billet goes into a furnace, huge, like a small room, and they gradually crank the temperature up to 2200 degrees Fahrenheit. The metal turns red, almost flowing, and when the blacksmith strikes it with a sledgehammer, you hear a deep, resonant boom that vibrates through the floor. Here, timing is everything. Too fast and the metal can crack. Too slow and it cools down, turning hard and unworkable. Precision matters here, and the forge crew knows this by heart. One holds the workpiece in place, another swings the hammer, a third monitors temperature and shape. Every movement is honed by years of practice, and even the smallest mistake can ruin the entire job. When the workpiece becomes pliable, rough shaping begins. They use massive hammers weighing several hundred pounds, controlled by overhead cranes. Strike after strike, the metal gets stretched and expanded, taking the shape of the future wrench. Sparks spray out in fans, and after each blow, a characteristic dent remains on the surface. The next strike integrates it into the overall geometry. You can already make out where the handle will be and where the working jaw for the nut goes. The process takes several days because the metal gradually cools and needs constant reheating to avoid internal stresses and cracks. Each heating and forging cycle brings the workpiece closer to the right shape, but there's no rushing it. Steel doesn't forgive haste. After rough shaping comes precision forging. The blacksmiths work with smaller hammers and specialized dies. The working jaw gets fitted to the exact nut size, the handle stretched to the required length and thickness. Every strike matters. Even a fraction of a millimeter off can ruin the tool. Checking happens constantly. The masters use templates over 6 feet long, gauges for thickness control, straight edges to verify surface flatness. At this stage, the blank gets heated and cooled several more times. Each cycle relieves internal stresses and refines the form. The team works like a single machine. One delivers the blows, another monitors the shape, a third makes sure the metal doesn't overheat and start losing its structure. This isn't just physical labor, it's true craftsmanship. A blacksmith's eye sees what no instrument can: a barely noticeable warp, a slight thickening, microscopic curvature. All of it gets corrected here, on the anvil, while the metal's still hot and cooperative. Next comes heat treatment, one of the most critical stages. The wrench is heated to over 1,800 degrees Fahrenheit, then rapidly cooled in massive oil baths. The moment of immersion is a spectacle in itself. The oil boils, a column of vapor rises, and for a few seconds the shop floor looks like it's shrouded in fog. This makes the metal hard and durable, but also brittle. So immediately after quenching, they perform tempering, reheating to several hundred degrees and slow, gradual cooling. This gives the metal the optimal balance between hardness and flexibility. During this process, the steel literally breathes. You can see it change color from cherry red to deep blue and finally to steel gray. And with each transition, it gets closer to that state where it's ready to handle incredible loads. Manufacturing one of these giant wrenches takes several weeks, sometimes up to 3 or 4, depending on the complexity of the order and the size of the piece. Most of the time is consumed by heating and rough shaping, which are done in stages, with repeated heating and cooling to avoid cracking. After heat treatment comes grinding and polishing. The smiths use large abrasive wheels and cutters to give the wrench a smooth surface and precise dimensions. First, they strip off the rough layer of scale that formed during heating. The metal underneath gleams with fresh steel. Then they polish the handle, fit the working jaw to the nut, check every millimeter against templates. It's striking how much time goes into details that at first glance seem invisible. Rounded edges to prevent burrs, chamfers in the jaw corners, perfect parallelism of the faces. Here, it's not just precision that matters, but the sequence of operations. That's what determines the tool's reliability and the future user's safety. When the wrench is ready, they move it to the test stand. It gets clamped onto giant bolts, and they visibly check how the metal reacts to enormous loads. Engineers monitor deformation, measure deflection, hunt for micro cracks using ultrasonic scanners. They ramp up the load in stages, from minimum to rated and beyond, to confirm the safety margin. You stand nearby, and it's hard to look away as a chunk of metal transforms into a powerful, precision instrument. Here you feel the full scale of industrial work, from furnace temperature to hammer blows to grinding accuracy. At the final stage, craftsmen move on to what seems simple from the outside, but is actually a critically important part of the job: protecting the metal and preparing the tool for use. After weeks of forging, heating, grinding, and polishing, the steel is still vulnerable to external factors. Air, moisture, even oil residue from hands can trigger corrosion. And for a tool of this scale, that means the risk of cracks, deformation, and loss of precision. The craftsmen start by applying a special protective coating to the entire metal body of the wrench. This isn't ordinary paint. They use anti-corrosive compounds and lacquers that penetrate the steel's micropores and form a tough protective film. The coating has to withstand impacts and contact with aggressive fluids the tool will encounter in production. They work with brushes and sprayers, making sure the layer goes on evenly across the entire surface, including the interior parts of the jaw opening and hard-to-reach areas of the handle. If the coating goes on uneven or leaves gaps, that's exactly where corrosion can start down the road, and all this massive work gets put at risk. After applying the protective layer, they paint the tool's handle with special paint. It's not just about making the wrench look good. The paint's designed to improve grip, prevent hands from slipping, and shield the surface from scratches and grime during use. For wrenches this size, they use paint that can handle serious mechanical stress, sudden temperature swings, and contact with oils and lubricants used in factories. Usually they apply 2 or 3 coats, letting each one dry. That's how you get a dense, wear-resistant finish. After painting, they let the coating air dry naturally, takes up to 24 hours, then check it's even by running a special probe across the surface. This step might seem cosmetic, but it's actually critical. Its quality determines how long the wrench lasts, how safe it is to work with, and how precisely it turns those giant nuts. Only after every protection step is complete can the tool be considered fully ready. It's packed into special wooden crates with soft padding to prevent the coating from getting damaged during shipping, then sent off to the customer. Throughout the tour, I kept marveling at how metal transforms in people's hands into an object capable of turning nuts weighing hundreds of pounds while staying precise and controllable. From red-hot blank to lacquered finished product, every step is filled with craftsmanship, physical labor, and engineering ingenuity. These wrenches work for decades, and every time a technician grabs the handle, they're trusting this tool with their safety. This is a place where scale is measured in yards and tons, but precision in thousandths of an inch. And here, one cannot exist without the other. Picture this, a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands. scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break, doesn't bend, doesn't crack, for decades. How does a 4mm sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets, and I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes.
It all starts in the raw materials warehouse.
And the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport: chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts, with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part: forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method: shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a 3-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside, stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted. And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work: riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force. But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting. When all the parts are ready, assembly begins. The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. 2 enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets. After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly. That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, this structure started as a flat sheet barely 1/6 of an inch thick. And every fraction of that journey, someone's work, someone's inspection, someone's craft.
Today we're going on an incredible journey. From massive crankshafts that power ocean vessels to precision railroad components that keep millions of passengers safe. Settle in and let's dive into the mesmerizing world of industrial manufacturing. Here we're witnessing something truly impressive, the machining of a massive marine crankshaft weighing over 15 tons. This isn't your typical workshop project. These crankshafts are the beating heart of container ships and cruise liners, converting the explosive power of diesel engines into rotational motion that propels these ocean giants across our seas. The star of the show, a revolutionary vertical boring mill. Rising nearly 3 stories tall, this engineering marvel features a 20-foot diameter faceplate capable of machining parts up to 65 feet long. The machine's spindle delivers an impressive 1,600 horsepower while maintaining accuracy tolerances of just 4/10,000ths of an inch. That's thinner than a human hair. An advanced computer numerical control system coordinates up to 12 simultaneous axes, ensuring every cut is executed with mathematical precision. Watch as the massive crankshaft rotates at a carefully controlled speed of 15 revolutions per minute. Carbide cutting tools, each costing more than a luxury car, slice through hardened steel like butter. The cooling system pumps 500 gallons per minute of specialized cutting fluid, preventing thermal distortion while washing away chips that look more like metal ribbons. Notice how the operator monitors vibration sensors and thermal cameras. At this scale, even tiny deviations can spell disaster. The real magic happens during the finishing passes. Using diamond-tipped tools, surface finish reaches an incredible 0.4 microns, smoother than a mirror. Laser measurement systems continuously verify dimensions, while ultrasonic testing ensures the internal structure remains intact. This single crankshaft will operate for decades, generating millions of horsepower cycles. It's a testament to German engineering precision that transforms raw steel into a mechanical masterpiece worth over $500,000. Welcome to where they've redefined what heavy-duty really means. This isn't just another CNC lathe. This is a mechanical monster engineered to tackle the roughest, toughest machining jobs in heavy industry. When aerospace manufacturers need to machine titanium landing gear components, or when power plants require custom turbine shafts, this is where they turn. This beast can handle parts up to 5 feet in diameter and 40 feet long, weighing up to 25 tons. The main spindle generates 400 horsepower through a precision planetary gearbox, delivering massive torque at low speeds. Watch the machine attack this massive steel workpiece with aggressive roughing cuts. The cutting parameters are mind-blowing. Depth of cut just over ½ an inch, feed rate around a 32nd of an inch per revolution, removing over 200 cubic inches of material per minute. High-pressure coolant jets at 1,000 pounds per square inch blast away continuous ribbons of steel chips that could fill a pickup bed in just minutes. Advanced vibration damping and thermal compensation systems maintain dimensional accuracy within 0.02 of an inch across the entire part length. The CNC system with adaptive control technology automatically adjusts cutting parameters based on real-time force and temperature feedback. It's like having a master machinist intuition built right into the machine's brain. Step into the world of railroad wheel manufacturing, where safety and precision aren't just priorities, they're matters of life and death. Every single day, millions of passengers trust their lives to these wheels, which must withstand enormous forces, extreme temperatures, and millions of rotation cycles. From high-speed trains racing across the European countryside to heavy freight locomotives hauling cargo across the American plains, the wheels we're about to see represent the culmination of over 150 years of railroad engineering evolution. Our journey begins with carefully selected steel billets, heated to a blazing 2,190 degrees Fahrenheit in massive induction furnaces. Watch as the glowing steel is shaped by 8,000-ton forging presses that deliver forces equivalent to the weight of 800 elephants. This forging process aligns the steel's grain structure, creating the incredible strength needed to support railcars weighing 25 tons. The wheels are then normalized in computer-controlled furnaces, cooling slowly over 48 hours to achieve the perfect balance of hardness and toughness. Quality control begins immediately. Ultrasonic testing reveals any internal defects that could prove catastrophic in service. Now the precision work begins. Each wheel blank is mounted on state-of-the-art CNC wheel lathes, masterpieces of German engineering capable of maintaining tolerances tighter than the thickness of paper. These machines feature massive chucks 10 feet in diameter that grip the wheel with hydraulic pressure equivalent to 50 car jacks. The cutting tools are specially designed carbide inserts, each costing $200 and engineered to maintain sharp edges through thousands of cuts. Computer vision systems scan each wheel, creating a three-dimensional map that guides the machining process. This is where artistry meets engineering. The wheel profile isn't just a simple curve, it's a complex mathematical shape that determines how the train will ride, steer, and brake. Watch as the lathe creates the tread surface with its precise 1-in-20 taper, the flange that keeps the train on the rails, and the intricate root radius that prevents stress concentrations. Each cut is monitored by laser sensors measuring to within 0.01 millimeters. Surface finish must be perfect. Any imperfections will create wear that could lead to derailment at 200 miles per hour. Here we're looking at one of the most demanding machining operations out there, boring and facing an 8-inch diameter hole through massive steel components. This isn't your typical drilling operation. We're talking about creating precision holes through materials that could stop a tank round. These operations are common in heavy industrial applications like hydraulic cylinders for mining equipment, deep hole drilling for oil drilling, and cylinder blocks for massive diesel engines. The horizontal boring mill dominates this operation with its massive spindle assembly, capable of reaching several feet into the workpiece. The boring bar itself, a precision tool weighing hundreds of pounds, must remain absolutely rigid while cutting forces try to deflect it. Advanced vibration damping systems and precision spindle bearings ensure cutting tool stability. The cutting insert, $300 of carbide engineering, must maintain a sharp edge while removing cubic inches of steel per minute. Watch as a massive cutting tool begins its journey through steel, creating this perfect 8-inch hole. The cutting parameters are carefully calculated. Too aggressive, and the boring bar will deflect. Too conservative, and productivity suffers. High-pressure coolant floods the cutting zone, not just for cooling, but to flush away the continuous stream of steel chips that could jam the operation. The machine's computer numerical control system automatically compensates for boring bar deflection, ensuring the final hole diameter stays within a tolerance of 0.01 inches across its entire length. Now comes facing, creating a perfectly flat surface perpendicular to the hole. The facing head, equipped with multiple cutting inserts, machines the surface at feed rates measured in thousandths of an inch. Once complete, this component could become part of a mining excavator's hydraulic cylinder, where it'll control movements of machinery weighing hundreds of tons. The precision we just witnessed ensures these systems run reliably for decades, moving mountains one bucket at a time. Our final segment showcases the artistry of complex turning operations, creating intricate threaded components that combine multiple diameters, sophisticated geometries, and precision threads in a single setup. These parts might look simple, but they represent the pinnacle of machining mastery, demanding perfect coordination of cutting tools, spindle speeds, and feed rates to achieve dimensional perfection across every feature. This component features multiple turned diameters, each with different tolerances and surface finish requirements. Notice the stepped geometry requiring different cutting tools for each operation, the internal threading that must align perfectly with external features, and the complex radii that seamlessly blend surfaces. The threading operation demands specialized thread cutting tools and precise spindle synchronization. The computer numerical control system coordinates spindle speed with carriage speed to create perfect thread pitch. Tool changes happen automatically, each cutting insert optimized for its specific operation. Single-point threading tools carve helical grooves with mathematical precision, creating threads that will mate perfectly with corresponding components. Thread pitch accuracy within 0.0001 inches, correct thread form angles, and perfect surface finish all combine to create threads exceeding commercial standards. The completed part undergoes comprehensive quality inspection using specialized thread gauges, optical comparators, and coordinate measuring machines. Every dimension, thread specification, and surface finish gets verified against engineering drawings. These complex turned parts often become critical components in aerospace applications, medical devices, or precision instruments, where failure isn't an option. "60 days. That's exactly how long it takes for an empty Coke can to become a brand new can on a store shelf. You finish your drink, toss the can in the trash, and 2 months later that same can is back in the supermarket. But this isn't magic. It's aluminum recycling, the most profitable recycling process on the planet. Every recycled can saves 95% of the energy compared to making new aluminum. It's like the difference between taking a walk and flying to another continent. Every year, 600 billion aluminum cans get recycled worldwide. Weight, 20 million tons. Value, $50 billion. And here's the most amazing part. Aluminum can be recycled infinitely, without losing quality. Metal that's been melted down 1,000 times is identical to fresh aluminum. How is that possible? How does a dirty crushed can turn into a perfectly clean sheet of metal? Stick around till the end. You'll see the most perfect closed-loop system ever created by humans. Every second, 20,000 aluminum cans get tossed worldwide. In a minute, over 1 million. In a day, 1.5 billion. That's a mountain of metal as tall as Everest, and all of it needs collecting, sorting, recycling. The process starts on city streets. Blue-marked trash bins wide for recyclables. Trucks gather the contents and haul them to sorting facilities. Conveyor belts here stretch over 300 feet. Everything moves down the line: cans, bottles, cardboard, plastic. The job? Separate aluminum from everything else. And this is where technology kicks in. Powerful electromagnets hang above the conveyor. But aluminum isn't magnetic. So how do you pull it out? The magnets create eddy currents. A rapidly changing magnetic field induces a current in the aluminum, and that current creates its own field. This field repels the cans away from the conveyor. They literally jump up and fly into a separate bin. One separator processes 15 tons of trash per hour. Pure aluminum drops into the collector. Everything else keeps moving down the line. Next up, cleaning and prep. Cans arrive dirty. Beverage residue, labels, paint. All of it's gotta go. Cans get loaded into massive drums. 10 feet across, 30 feet long. Inside, water and alkaline solution. The drum spins. Cans scrub against each other. Dirt, labels, paint wash away. Water drains through filters, leaves nothing but clean metal. Then drying. Hot air at 300 degrees. Fahrenheit evaporates moisture in 15 minutes. Now the cans need compressing. A hydraulic press generates 300 tons of pressure. 1,000 cans become a dense block weighing 45 pounds. These blocks are called bales, easy to store and transport. A truck can haul 15 tons of bales. That's 750,000 cans. Bales get stacked in open yards. Aluminum doesn't rust, rain can't hurt it. It waits its turn for remelting. Some blocks sit a week, others a month. But they all end up in the same place eventually, the melting furnace. (1827). German chemist Friedrich Wöhler produces pure aluminum for the first time. Tiny beads of silvery metal. Light as wood, but strong as iron. Beautiful as silver, but it doesn't tarnish. The world goes crazy. Aluminum gets called the metal of kings. Its price, $1,200 per kilogram. That's 3 times more expensive than gold. French Emperor Napoleon III orders aluminum silverware for his most important guests. Everyone else eats with gold, it's cheaper. The problem is, aluminum is incredibly hard to extract. It's hidden in ore, bauxite. Extracting it chemically is nearly impossible. You need tons of reagents and weeks of work for a single gram of metal. Things change in 1886. American Charles Hall and Frenchman Paul Héroult independently invent the electrolytic process. You run current through molten ore. You get pure aluminum. Simple, fast, cheap. The price drops from $1,000 to $2 in 20 years. The aluminum revolution begins. The 20th century turned aluminum into the planet's most widely used non-ferrous metal. Airplanes, cars, electrical wiring, beverage cans, aluminum everywhere. By the 70s, global production hits 10 million tons a year. But there's a problem. Producing aluminum from ore demands monstrous amounts of energy. To get 1 ton of metal, you need 15,000 kilowatt hours of electricity. That's a year's worth of power for the average American home. Plus carbon dioxide emissions, landscape destruction from open pit mines. Environmentalists sound the alarm. Then someone grasps the obvious. Aluminum doesn't degrade. A can tossed in the forest will sit there 200 years unchanged. But what if you melt it down? Energy cost? Just 700 kilowatt hours per ton. 20 times the savings. No need to mine ore, no need for chemical reagents, no need for giant electrolyzers. Just melt the metal and use it again. The recycling era begins. In the US during the 70s, 15% of cans got recycled. Now, 50%. In Brazil, 98%. That's the highest recycling rate of any material. The smelting shop. Air temperature near the ceiling, 122 degrees Fahrenheit. In the center of the hall stands a furnace as tall as a 3-story building. They call it a reverberatory furnace. Inside, a bath of molten aluminum. Temperature, 1400 degrees Fahrenheit. The metal glows orange. Heat dances above it. Briquettes feed in by conveyor straight into the furnace. The aluminum melts instantly, melting point. Just 1220 degrees. That's 2.5 times less than steel. The energy savings are massive, but trash floats in the melt. Paint residue, varnish, impurities from other metals. They need to be removed. Chlorine gets blown into the bath. The gas rises in bubbles through the melt. It binds the impurities and carries them to the surface. Dross forms, gray foam. It's scraped off with mechanical rakes. Beneath the dross, a mirror of pure metal. After 6 hours of melting, the furnace is ready to tap. A massive ladle rolls in from below. The furnace tilts and the melt pours out in a golden stream. One ladle holds 20 tons. That's 1 million cans in liquid form. The molten metal gets poured from the ladle into molds. Out come ingots weighing 25 tons each. Length, 33 feet. Width, 5 feet. Thickness, 20 inches. They cool for 24 hours. Temperature drops from 1300 degrees Fahrenheit to room temperature. The ingot solidifies but stays soft and pliable. That's aluminum for you. It deforms easily. Next stage, rolling. The ingot heads to the rolling mill. This giant machine has rollers 6.5 feet across. The ingot passes between the rollers. Pressure, 1,000 tons. The metal flattens like dough. In one pass, thickness shrinks from 20 inches to 8. The ingot passes through the rollers again. Now it's 4 inches thick. Another pass, 2 inches. Another, under an inch. The process repeats 20 times. At the end, you get a sheet about 1/10 of an inch thick. It comes out of the mill over 1/2 mile long, rolled into a coil weighing 10 tons. One coil makes 30,000 cans. The metal ships to the packaging plant. There they stamp blanks from the sheet, stretch the walls, form the neck. Circle complete. 60 days after hitting the trash, the can's back on the shelf. And that's how aluminum lives forever. The metal atoms in your Coke can right now might have been part of a World War II aircraft. Then became a house roof in the 50s. Then power line cables in the 80s. Then a bicycle frame in the 2000s. And now, a can in your hand. Tomorrow, they'll become part of a laptop. The day after, the skin of a spacecraft. Aluminum doesn't know aging. Each remelt returns its youth. It's the only material on the planet that can be used infinitely without degrading. Humanity produces 100 million tons of aluminum a year. 75% of all the metal ever produced is still in use today. Imagine, metal cast 100 years ago is working right now. Aluminum recycling isn't just waste processing, it's a philosophy of matter's immortality. Proof that in the right hands, the planet's resources are inexhaustible. Every can you toss isn't trash. It's a stockpile of metal for future generations. A closed loop, eternal rebirth. Aluminum will outlive civilizations and will serve those who come after us.
The Caterpillar 3618 engine, 18 cylinders, 88 gallons of displacement, 7,200 kilowatts of power, 9,655 horsepower. One engine weighs 79,000 pounds. The piston in this engine, 11 inches in diameter, 11.8 inches of stroke, 50 pounds in weight. This is Caterpillar's largest piston. How do they make it from liquid aluminum? Today you'll see the complete production cycle of a giant piston, from an aluminum ingot to a part that moves at 33 feet per second and withstands 2,685 psi. If you want to see how they make the heart of a giant engine, subscribe to the channel. Here we show you the factories that move the world. The Caterpillar 3618 engine is designed for high-speed marine vessels, ferries, patrol boats, yachts. A single engine produces 9,655 horsepower at 1,050 revolutions per minute. It's a V18 four-stroke diesel. Cylinder bore is 11 inches. Stroke is 11.8 inches. Displacement per cylinder is 1,130 cubic inches. 18 cylinders total, 20,330 cubic inches. Compression ratio 12.6 to 1. Maximum cylinder pressure 2,680 psi. That's 185 atmospheres. Combustion chamber temperature 3,600 degrees Fahrenheit. Mean piston speed 34.4 feet per second. The piston travels 11.8 inches in 0.028 seconds. Up and down 1,050 times per minute. 70 million cycles over 10,000 hours of operation. The piston material has to withstand all of that.
The piston is made from an aluminum alloy.
Aluminum is lightweight, density of 169 pounds per cubic foot. That's 3 times lighter than steel. Aluminum conducts heat well. Thermal conductivity of 133 BTU per hour per foot per degree Fahrenheit. That's 5 times better than steel. They use alloy 2618. Composition: 92% aluminum, 4% copper, 1.5% magnesium, 1% nickel, 1% silicon. Copper provides strength at high temperatures. Magnesium increases hardness. Nickel reduces thermal expansion. Silicon improves casting properties. The alloy arrives in ingots. Shape: a cylinder 12 inches in diameter, 3 feet 3 inches long. Ingot weight: 353 pounds. Before forging, the ingot is cut into blanks. Blank length: 12 inches. Weight: 84 pounds. This is the blank for one piston with extra material for machining. The blank gets loaded into an induction furnace. Temperature: 895 degrees Fahrenheit. Heat time: 30 minutes. The aluminum softens. Doesn't melt. Melting happens at 1220 degrees. We need plasticity for forging. The heated blank transfers to a forging press. Hydraulic press. Force: 10,000 tons. That's 100 meganewtons. The blank sits in the lower die. Die made from heat-resistant steel. The upper die descends from above. The press creates pressure. Aluminum flows, fills the die cavity, takes the shape of a piston. The process is called backward extrusion. Metal flows upward around the punch, forms the piston skirt. Pressure climbs to 10,000 tons. Forging time: 12 seconds. Metal densifies. Grains align along stress lines. This makes the piston strong. Forging increases strength 30% compared to casting. After forging, the press opens. Piston extracted. It's hot, 750 degrees. Weight: 66 pounds. Shape's close to final, but machining still needed. Heat treatment. The forged piston goes into the hardening furnace. Temperature: 986 degrees Fahrenheit. Hold time: 8 hours. Copper and magnesium dissolve into the aluminum. The structure becomes uniform. Then, rapid cooling in water. Water temperature: 68 degrees. Cooling rate: 180 degrees per second. Copper and magnesium don't have time to precipitate out. They're trapped in the lattice. Strengthening zones form. After quenching, the piston is soft. Hardness: 60 on the Brinell scale. Artificial aging is needed. The piston is heated again. Temperature: 374 degrees. Time: 16 hours. Copper and magnesium precipitate from the lattice as fine particles. They strengthen the aluminum. Hardness climbs to 135 on the Brinell scale. Strength reaches 65,000 pounds per square inch. Elongation: 10%. The piston is strong and ductile at the same time. Machining begins with the turning operation. The piston gets clamped into the chuck of a CNC lathe. The chuck diameter is 19.7 inches. Spindle speed is 300 revolutions per minute. The cutting tool is carbide, tungsten carbide. They machine the outer surface of the skirt. Final diameter is 11.02 inches. Tolerance, plus or minus 0.0008 inches. Skirt taper, 0.002 inches per inch of length. This compensates for thermal expansion. Cutting speed is 490 feet per minute. Feed rate is 0.008 inches per revolution. Depth of cut is 0.02 inches. They remove 0.28 inches from the diameter. Machining time is 20 minutes. The surface is smooth. Surface roughness is 63 micro-inches. Then they mill the ring grooves. 3 grooves. Width of the first is 0.16 inches. Second is 0.14. Third is 0.2 inches. Depth of the first is 0.31 inches. Milling cutter diameter is 4 inches. Spindle speed is 1200 revolutions per minute. Groove accuracy plus or minus 0.0004 inches. They're drilling the hole for the piston pin. Hole diameter, 4.33 inches. Depth, 7.87 inches. Carbide drill bit. Rotation speed, 500 revolutions per minute. Feed rate, 0.006 inches per revolution. Drilling time, 8 minutes. After drilling, reaming. The reamer brings the diameter to 4.3302 inches. Tolerance, plus 0.0004 inches, minus 0. Surface roughness, 0.315 thousandths of an inch. This is an interference fit for the bronze bushing. The bushing gets press fit with 10 tons of force. Interference, 0.0012 inches. They mill the oil channels. 2 channels, diameter 0.47 inches, running from the crown to the skirt. They carry oil away for cooling. They drill the oil jets. Diameter, 0.079 inches. 8 of them around the crown circumference. Oil sprays through them onto the inner surface. Cooling is critical. Crown temperature hits 662 degrees Fahrenheit. The oil carries the heat away. Machining the combustion chamber. The piston crown gets milled on a 5-axis machine. The combustion chamber has a complex shape. A toroidal cavity, diameter 7.1 inches, depth 2 inches, chamber volume 0.3 gallons. The shape's optimized for mixing fuel with air. Ball nose cutter, diameter 0.8 inches. Spindle speed 3,000 revolutions per minute. Tool path spirals from center to edge. Spiral pitch 0.02 inches. Machining time 40 minutes. Surface roughness 0.00016 inches. Then chamber polishing. Abrasive paste, 3-micron grit. Polished with a felt wheel. Speed 1,000 revolutions per minute. Time 5 minutes. The polished surface prevents carbon buildup. Final operation, honing the skirt. Honing creates a crosshatch pattern of micro grooves. Angle 60 degrees. Groove depth 0.00012 inches. Width 0.0008 inches. These grooves retain the oil film, reduce friction. Honing time 10 minutes. Coatings and inspection. The crown gets a ceramic thermal barrier coating. Thickness, 0.3 millimeters. Material, yttria stabilized zirconia. Thermal conductivity, 2 watts per meter Kelvin. That's 100 times less than aluminum. The coating drops the crown temperature by 100 degrees. Applied by plasma spray. Plasma temperature, 10,000 degrees. Particle velocity, 1,000 feet per second. The skirt gets a graphite coating, anti-friction. Thickness, 0.015 millimeters. Cuts friction by 40%. Reduces wear at startup. Ring grooves get hard anodized. Hard anodization. Layer thickness, 0.05 millimeters. Hardness, 500 Vickers. Protection against ring wear. Every piston gets inspected. Diameter measured at 6 points. Laser micrometer. Accuracy, 0.001 millimeters. Weight gets checked. Scale accurate to 1 gram. Tolerance, plus or minus 5 grams. Weight variance in a set, no more than 10 grams. For engine balancing. X-ray checks internal defects, cracks, porosity, inclusions. Rejection rate, 0.5%. Finished piston weighs 51 pounds. Diameter, 11 inches. Height, 13.8 inches. It'll run 10,000 hours, 70 million cycles. Handle temperatures of 350 degrees. Pressure, 185 bar. Speed, 33 feet per second. That's how Caterpillar makes the biggest pistons. From aluminum ingot to a component that holds 9,000 horsepower. If this was interesting, hit that like button. Comment what engines you know. Subscribe. Here we show you how giants get made.
Imagine a river of white-hot metal as bright as the sun, born inside a giant furnace, melting everything in its path. But did you know that to create 1 ton of iron, you need almost 2 tons of rock and coal? It seems like alchemy. Hundreds of kilograms of oxygen and impurities vanish from dirty ore, leaving only pure metal behind. In the US, just a handful of these furnaces produce over 25 million tons a year, enough to build 250 aircraft carriers. And yet, there is a secret hidden within this story, one that will only be revealed to those who watch until the very end. It all begins deep in a quarry, where iron ore is mined. This isn't metal, but reddish-brown rock that looks like rusty earth. The iron is tightly bonded with oxygen, and the primary mission is to break that bond, liberating the metal within. Along with the ore, 2 other key ingredients for this infernal recipe arrive at the plant. The first is coke, a specially processed form of coal. It's baked in an oxygen-free oven to remove all impurities, resulting in pure, porous carbon that burns with incredible heat. In our process, coke is both the fuel and the main chemical agent. The third ingredient is limestone, a common rock. Its role? It's the cleaner. When heated, the limestone will act as a magnet for all the waste, collecting it into a separate mass. Now, let's go to the plant to meet the hero of our story, the blast furnace. It's a tower over 30 meters high, lined entirely with fireproof brick and wrapped in a network of pipes. This tower never sleeps. It runs continuously 24 hours a day, sometimes for years without stopping. It is a giant stomach that must be constantly fed. From the top, using a special skip hoist that looks like a small rail car, our ingredients are charged into the furnace. Not just thrown in, but layered like an industrial lasagna. A layer of coke, then a layer of iron ore and limestone, another layer of coke, and so on. To get 1 ton of liquid iron, you need to load almost 2 tons of raw material into the furnace. This figure includes the iron ore, the coke, and the limestone. It shows just how efficiently a blast furnace works as a giant filter. It takes nearly 2 tons of rock and coal, burns away everything unnecessary, and yields 1 ton of pure, concentrated metal. This is true industrial alchemy. Once the furnace is fed, the heat is turned up. At the bottom of the furnace are special nozzles called tuyères. Through them, air is blasted in under immense pressure, superheated to 1100 degrees Celsius. This hot blast ignites the coke, causing it to burn with incredible ferocity. The entire mass of materials loaded from the top begins its long journey down through zones of increasing temperature. First, in the upper section, hot gases rising from below dry and preheat the ore. A little further down, the chemistry begins. The burning coke reacts with oxygen to form carbon monoxide. And this carbon monoxide is our master thief. It greedily rises, meets the iron ore, and starts stripping away the oxygen atoms, leaving pure iron behind. About halfway down, the temperature becomes so intense that both the iron and the impurities begin to melt. This is where our cleaner, the limestone, comes into play. It decomposes and starts to bind with all the unwanted elements, forming a light molten mass called slag. At the very bottom of the furnace, in its heart, known as the hearth, a lake of two unmixable liquids forms. At the very bottom, being heavier, lies the pure molten iron, and floating on top, like oil on water, is the lighter molten slag. Every few hours, it's time for the tapping. A special machine, like a huge drill, pierces a hole in the fireproof lining of the furnace, first for the slag. A thick, bright orange river of molten rock erupts with a hiss. Once the slag is drained, the main event begins. The drill opens another hole slightly lower down, the iron notch. And from there, with a roar and a blinding glare, a torrent of molten metal is unleashed. It isn't orange, it's a brilliant white gold, so bright it's painful to look at without special glasses. The heat radiates from it, a physical force you can feel on your skin from dozens of meters away. This dazzling river of metal, throwing off fountains of sparks, flows down a long refractory channel into a huge mobile ladle shaped like a giant cigar on wheels, known as a torpedo car. This torpedo can hold several hundred tons of liquid metal and, like a thermos flask, keeps it hot while it's transported to the next stage. What we have created in the blast furnace is called pig iron. It contains a lot of carbon, which makes it very brittle. When the metal cools in the molds, it solidifies. After the mold is broken, a finished cast iron product is revealed. And so, from a cold, red rock through the fiery stomach of the blast furnace where chemistry and heat work their magic, this heavy, reliable, and durable material is born, ready to serve us in our daily lives. Each year, blast furnaces in the United States produce roughly 30 million tons of iron. It's a number so vast, it's hard to comprehend. Let's try. The average Nimitz-class aircraft carrier weighs about 100,000 tons. This means that in 1 year, American plants produce enough iron to build a fleet of 250 of them. Or to put it in more grounded terms, if we take the weight of an average passenger car, that's enough metal to make over 12 million vehicles. An entire automotive nation born in the fire of the blast furnaces in a single year. There are only about 15 blast furnaces currently operating in the entire country. We are not talking about thousands of small plants, but a small number of true titans. This means each of these towers is an incredibly productive monster. The average blast furnace in the U.S. produces over 5,000 tons of iron every single day. Over 90% of all pig iron produced in blast furnaces is not the final product. It is just the first step. This hot, carbon-rich metal is essentially the raw material for making steel. It is transported in torpedo cars to the next plant, where, in oxygen converters or electric furnaces, the excess carbon will be burned off, turning brittle iron into strong, ductile steel. So these 25 million tons of iron are the foundation from which skyscrapers will rise, bridges will be built, and cars, ships, and even simple tools will be made.
Today we're at one of Europe's largest oil extraction plants, where ordinary sunflower seeds become the very same oil sitting in your kitchen. The facility sprawls across dozens of acres, silos towering overhead, pipelines everywhere, tanks as far as you can see. And hanging over everything, this warm, slightly oily air with a nutty undertone. You'd think it's simple, just squeeze and done. But when you see the scale of this operation, you realize, between a seed from the field and that clear bottle on the store shelf, there's an entire chain of processes where temperatures hit 570 degrees Fahrenheit, pressure reaches hundreds of atmospheres, and raw material flows in at thousands of tons per day. Come on, let me show you how it all works. It all begins in the fall, when one grain truck after another rolls up to the plant from the fields. Each semi brings in 20 to 25 tons of sunflower seeds. At peak season, the plant receives up to 300 trucks a day. That's about 7,000 tons of raw material, every single day. But before a seed gets anywhere near production, it has to pass inspection. The lab at the entrance takes a sample from every truck with a long probe, stabbing into the grain pile at different depths. They check moisture, oil content, debris, and damaged seeds. Moisture can't exceed 7%, or the seeds will start rotting in storage.
Good sunflower seeds have an oil content of 45 to 52%, meaning almost half the seed is pure oil. If the parameters check out, the truck heads to unloading. The seeds pour into underground hoppers, where elevators lift them into silos, massive concrete towers up to 130 feet tall, where the raw material is stored under controlled temperature and ventilation. From the silos, seeds move along conveyors into the prep area. First step, cleaning. Seeds pass through separators that remove rocks, twigs, stem fragments, and other junk that hitched a ride from the field. Magnetic traps pull out stray metal bits, bolts, wire scraps, anything that could wreck the equipment. After cleaning comes cracking. Special mills split the hull and free the kernel. Think of it like cracking sunflower seeds with your teeth, except at tens of tons per hour. The hull, that's the shell we spit out when we snack on seeds, here they don't toss it. Hulls get pressed into pellets and burned in the plant's boilers, generating heat and steam for production. The facility basically heats itself with its own waste. The clean kernels get crushed on roller mills. Heavy steel rollers flatten them into thin flakes about 12 thousandths of an inch thick. That's called conditioning. The thinner the flake, the easier it is to extract oil later. Surface area multiplies. The meats get sent to roasters, massive multi-tiered vats where they're heated with steam to 200 to 230 degrees Fahrenheit while constantly stirring. This process is called moist heat treatment. It softens the cell walls and lets the oil flow out more easily. The smell in this room is incredible. Thick, nutty, warm, makes you instantly hungry. From the roasters, the hot meats feed into screw presses, powerful machines that look like giant meat grinders. Inside, a steel auger spins, forcing the mass through a narrowing channel. Pressure builds to 4,400 to 5,000 psi, and the oil literally gets squeezed out of the meats, dripping through slots in the press housing into a catch tray. A hot golden stream pours continuously. It's mesmerizing to watch. This is pressed oil, dark, cloudy, with a strong roasted seed smell. Many people think this is the final product,
But actually, the press only extracts about 60 to 65% of the oil. The rest hides in the cake, a dense compressed disc that comes out of the press hot and hard as wood.
To grab the remaining oil, the cake gets sent to extraction, and this is where the real chemistry begins. The cake is crushed, flattened again into flakes, and loaded into an extractor, a long horizontal unit that looks like a slowly rotating carousel. Inside, the flakes get washed with a solvent, usually hexane, a volatile liquid that dissolves fats but doesn't mix with water. Hexane flows through the layer of cake, soaking up the oil, and comes out the other end as micella, a blend of solvent and oil. The process takes about an hour, and during that time, hexane pulls out virtually all the remaining oil from the cake. The fat content in the spent meal drops to 1%. Meal is what's left of the seed after the double pressing. It's protein-rich, up to 46%, and goes into livestock feed. Essentially, from a single seed, the plant gets oil for people, protein feed for animals, and fuel from the hulls. Zero waste production at its finest.
Now we need to separate the oil and hexane. The micella is heated in distillers to 200 to 220 degrees Fahrenheit. The hexane evaporates, its vapors are captured, condensed, and returned back to the extractor. It runs in a closed loop with almost no losses. Solvent losses per ton of oil, just about 2 pounds. The rest goes back into the cycle. What remains is crude extracted oil, dark with a specific smell and tons of impurities. Phospholipids, waxes, free fatty acids, pigments. You definitely shouldn't drink it yet. Refining begins, a multi-stage purification that transforms this murky dark liquid into the clear oil we're used to. First step, hydration. Hot water is added to the oil, and the phospholipids swell and precipitate out as a sediment, which is separated in a centrifuge. The centrifuge spins up to several thousand revolutions per minute and splits the oil and sediment in seconds. This sediment, lecithin, is a highly valuable product used in the food and pharmaceutical industries. Next up, neutralization. They pump an alkaline solution into the oil that binds up free fatty acids. The result? Soap. Yes, actual soap. A centrifuge spins it out, then they rinse the oil with water to get rid of leftover alkali. After that comes bleaching. The oil gets mixed with bleaching clay that soaks up pigments like a sponge, pulling out the dark color. The clay settles, gets filtered off, and the oil turns pale yellow, almost clear. The final and most delicate step of refining is deodorization. The oil gets heated to 440 to 480 degrees Fahrenheit in a vacuum column at just 2 to 4 millibars of pressure, basically the vacuum of space. They blast live steam through the hot oil, and it carries away every last volatile compound responsible for smell and taste. The whole process takes an hour to an hour and a half. What comes out? Completely neutral oil. No taste, no aroma. That's exactly what we buy at the store with the label refined, deodorized. The finished oil is cooled and passed through polishing filters, ultrafine membranes that remove the last microscopic particles. The result? A crystal clear liquid that won't cloud even when stored in the fridge. From the filters, the oil flows into stainless steel storage tanks holding up to 5,000 cubic meters, where it's kept under a nitrogen atmosphere, so oxygen can't oxidize the product. The bottling line is a spectacle in itself. Machines blow plastic bottles from preforms right there on the factory floor, then immediately fill them with oil, screw on caps, slap on labels, and pack them into boxes. Speed? Up to 12,000 bottles per hour on a single line, and there are several lines. In a day, the plant can bottle over 500,000 bottles. Every batch goes through lab testing: acid number, peroxide number, moisture content, clarity, taste, and smell. If even one parameter falls outside spec, the entire batch gets sent back for re-refining.
The scale is staggering. A major European plant processes up to 2 million tons of sunflower seeds per year and produces around 800,000 tons of oil. Europe is one of the world's largest producers of sunflower oil, and a significant chunk of production gets exported to dozens of countries. When you're standing on the factory floor, watching that golden stream of oil continuously pouring into bottles, and outside another grain truck pulls up for unloading, you realize what a massive industry stands behind that simple bottle on your kitchen shelf. From a seed in the field to oil in a bottle, dozens of stages, hundreds of pieces of equipment, and thousands of people making sure every single drop meets the standard. And it all started with an ordinary sunflower that turned its head toward the sun somewhere in a field. Deep beneath the ground in Ohio sits a machine that holds up America's skies. The Mesta 50 press, a 36,000-ton monster that plunges 10 stories underground. It squeezes metal with 50,000 tons of force. That's the weight of 10 Eiffel Towers at once. Without this machine, the United States would have no F-35 fighter jet, no Boeing 787, and when a crack appeared on the press in 2009, the entire American aviation industry held its breath. Today we'll see how white-hot titanium transforms into fighter jet wings under the blow of a steel fist from the Cold War era, and why this machine, and no other, remains irreplaceable to American defense. If you stood outside the Alcoa plant in Cleveland, Ohio, you wouldn't see anything special. Just an ordinary industrial building, gray brick walls, pipes, trucks. But head underground and you enter a world where real power is born. The Mesta 50 doesn't sit on the ground, it's embedded into it. 100 feet down, 10 stories of concrete and steel. Why so deep? Because when 50,000 tons of force slams into metal, the earth shakes for half a mile in every direction. Without this colossal foundation, the press would punch through the ground like a knife through butter. This machine was built in 1955 at the height of the Cold War, and it's still running, almost 70 years. In that time, generations of aircraft have come and gone, materials have evolved, control systems have advanced, but the press remains, because nobody has built anything more powerful. If you're into stories like this about machines that change the world, subscribe to the channel right now and hit the bell so you don't miss the next one. America and the Soviet Union weren't just racing in space, they were racing for the sky. Whoever builds the best aircraft dominates the air. And the best aircraft need parts that can't be made with conventional methods. Picture a turbine blade from an F-35 fighter jet engine. This component is only about a foot long, but it spins at 10,000 revolutions per minute at temperatures exceeding 2,500 degrees Fahrenheit. No welded seam could handle that. It would fail in seconds. The blade has to be solid, forged from a single piece of titanium or nickel superalloy. That's exactly what the 50,000-ton press is for. It doesn't cut or weld, it crushes, takes a red-hot chunk of titanium and transforms it into the precise shape of a wing or blade in a single strike. Press forging doesn't just shape metal, it changes the metal's very structure. The crystalline grain of titanium gets refined and aligned along the part's contours, making it several times stronger than if you cast or machined the same part from stock. The process starts with prep. A titanium ingot heats up in a specialized furnace to 1760 degrees Fahrenheit. At that temperature, titanium becomes soft as clay, but keeps its incredible strength. The metal glows bright red, almost white. You can't look at it without special glasses. When the temperature hits the sweet spot, a robotic arm pulls out the glowing ingot and moves it to the press in seconds. Time is everything. If the titanium cools even 90 degrees, it becomes too hard and the press can't deform it. The operator literally has no room for delay. Every move from furnace to press is drilled to perfection. Decades of practice, hundreds of thousands of parts. They lay the ingot into the lower die, a massive steel form that mirrors the shape of the finished part. The dies themselves are made from special tool steel and cost hundreds of thousands of euros each. From above, the upper die drops, 330,000 pounds. And then the strike hits. 50,000 tons of force slams down onto white-hot titanium. To put that in perspective, imagine stacking 150 passenger jets on your desk, all at once. Hydraulic cylinders 8 feet in diameter generate pressure of 50,000 psi. That's 3,500 times atmospheric pressure. Under this monstrous force, titanium behaves strangely. It doesn't break. It doesn't crack. It flows. Metal atoms shift, sliding past one another, filling every microscopic corner of the die. In 3 seconds, a shapeless ingot transforms into a perfect replica of a wing spar or turbine blade. The entire factory shudders from the impact. Workers feel the vibration hundreds of feet away, like a minor earthquake. Operators at the press wear specialized ear protection. The sound of the strike reaches 130 decibels, louder than a jet taking off. The strike itself lasts no more than 3 seconds, but in those 3 seconds, something happens that would take hours of conventional machining, and the result is stronger. But the most amazing thing? The precision. Despite the savage force, the press controls the shape to within half a millimeter. Laser sensors track every movement of the die. Hydraulics adjust pressure thousands of times per second. If something goes wrong, a part worth 300,000 euros turns into scrap metal. Mesta 50 produces parts for all major American aircraft: F-35 and F-22 fighters, Boeing 787, Apache helicopter engines. They all carry parts born under the blow of this press. Every month, more than 2,000 tons of titanium and nickel superalloys pass through it. The plant employs hundreds of specialists, metallurgists, press operators, quality control engineers. Each finished part undergoes rigorous inspection: ultrasonic scanning, X-ray, geometry measurement, accurate to hundredths of a millimeter. Documentation for each part is stored for decades. If a plane crashes, investigators can reconstruct the entire manufacturing history of every component. Only after passing all inspections does a part receive clearance for installation on an aircraft. And then disaster struck. In 2009, during a routine press operation, engineers heard an unusual sound: metal cracking. The press was immediately shut down. Inspection revealed something terrifying. A crack nearly 4 feet long had appeared in the main support beam. For the U.S. aviation industry, this was a real shock. Mesta 50, the only press of this power in the country, without it, F-35 production stopped. Boeing couldn't manufacture parts for the Dreamliner. Military contracts were frozen. Every day of downtime cost millions of dollars. The problem was that a 2,000-ton beam can't just be removed and replaced. It's installed in the structure at a depth of 100 feet, surrounded by dozens of other systems. And building a new press of equal power, that's years of work and billions of dollars. The country had neither. Engineers would have to repair it right there on site, 100 feet down, in cramped conditions with no way to extract the structure. A desperate repair effort began. A specialized team of welders worked around the clock for 4 months. They used cutting-edge technology, electroslag welding in an inert atmosphere. The crack was welded layer by layer, each about 1/8 of an inch thick. After each layer, the metal underwent heat treatment to relieve internal stresses. In total, 760 weld layers were laid down. Meanwhile, a backup beam was being fabricated, just in case the repair failed. It was made at another facility and delivered using America's largest crane, capable of lifting 4,000 tons. In December 2009, Site 50 was operational again. 200 engineers watched the first strike after repair. Everyone held their breath. The press struck. The facility shuddered. The titanium deformed precisely to the die shape, and the crack didn't reappear. 4 months of work, 760 weld layers, thousands of hours of heat treatment. It all held. The American sky was saved. Today, the 50 is still running. It's almost 70 years old now, an incredible age for industrial equipment. Modern presses are more efficient and automated, but none reach this kind of force. 50,000 tons remains an unbeaten record for the entire country. The 50 is more than just a machine. It's a symbol of industrial might and engineering determination. Every plane you see in the sky, every military fighter, every wide-body airliner, its structure contains parts born right here, beneath the Ohio ground, under the strike of this steel fist. Over the decades, an entire ecosystem has formed around the press. Thousands of engineers, metallurgists, operators who pass down from generation to generation the knowledge of how to work with this monster. It's proof that sometimes the best solutions aren't the newest ones, but those proven by decades of reliable work under incredible pressure. Literally. This ship doesn't go around the ice, it goes straight through it. 10 feet of frozen ocean, and it doesn't care. I'm standing in a shipyard where they're assembling the hull of a nuclear-powered icebreaker, and in front of me is a giant steel skeleton that will soon be working where temperatures drop below -50, and ice pressure can crush any ordinary structure like a tin can. You know, I usually go look at things you can touch without risking your cheek freezing to them, but today I slightly overestimated my ambitions. And right now, I'm going to show you how a machine is born that makes even the Arctic itself back down. The first thing that hits you at the shipyard isn't the size, though the future vessel stretches over 500 feet long, and individual hull plates run several inches thick. What stuns you is the steel itself. They don't use ordinary rolled stock here. An icebreaker hull demands special steel grades that stay flexible even in brutal cold. Regular steel turns brittle in the freeze. Strike it, and it'll crack like glass. This stuff, though, has to take impacts from ice fields and not fail. The engineers explain it simply. The hull needs to give a little, flex slightly under pressure. Otherwise, the Arctic will just snap it. Massive steel plates arrive at the yard already rough processed from the rolling mill. Each plate weighs dozens of tons, and when the crane lifts one into the air, it looks like a chunk of an apartment building somebody randomly decided to relocate. But the icebreaker's shape doesn't appear all at once. First, these plates pass through giant rollers that slowly, with enormous force, bend them to the required angle, giving the metal that crucial curve without which the hull can't push ice aside. In front of me, steel rollers, each as thick as a decent tree trunk, stacked one above the other. Between them, they slowly feed a flat steel sheet. Heavy, rigid, seemingly completely inflexible at first glance. The operator gives the command, and the mechanism starts moving. The rollers rotate at low speed, but with massive force. The sheet gradually gets pulled inside, and at some point, you can see it start to change shape. First, it's a barely noticeable bend. Then the radius increases, and the metal's no longer flat. It curves smoothly, as if obeying someone's will. The sound here is unique, a muffled pressure, grinding, and a slight crackling. like the metal reluctantly gives in. I'm standing nearby and I hear how the steel literally groans under the load, a sound like you're pressing on something really stubborn and it's grudgingly surrendering. They might roll the sheet several times, adjusting the roller positions each time until they get the exact angle or curvature. And there in front of you is no longer just a piece of steel, but part of a future hull that perfectly matches its contours. By the way, if you're into stories about how seriously complex and powerful machines are built, hit subscribe so you don't miss the next episode. Now, let's keep going. Next comes the assembly of sections, and this looks like a giant construction set, except each block weighs as much as a small locomotive. Individual hull blocks are assembled in the shop. These can be sections 60 or even 100 feet long. Inside each block, there are already bulkheads, cable routes, and even foundations for future decks. In other words, the hull isn't built from scratch in one spot. It's assembled in pieces, like a puzzle, just really heavy and really hot to produce. I walk into the shop and there are finished sections already standing there. These aren't just sheets of metal, they're entire fragments of the future ship. Inside each one, you can see passageways, openings for cables, spots where pipes, wires, and entire life support systems will run later. Then these blocks are transported to the slipway and joined together. The cranes move in. They lift the section into the air slowly, smoothly, no sudden movements, and transport it to the slipway. There, they carefully lower it and fit it against the already installed parts of the hull. At this moment, you literally see separate pieces starting to come together as one. The future icebreaker takes shape right before your eyes. Welding is a whole different story. You can't just run a bead and go grab coffee. Every joint goes through multiple levels of inspection. First, the welder lays the main seam. Then they check it with ultrasound to make sure there are no voids or cracks inside. If something's off, they cut it out and do it over. I watched them redo one seam 3 times, and nobody even got stressed. That's standard practice here, because the price of a mistake in the Arctic isn't just a breakdown, it's a potential catastrophe. And that's how it goes. Every seam, every joint, along the entire length of the hull. We should talk about the hull shape. An icebreaker doesn't just have a strong bow, it's specifically designed to climb up onto the ice and break it with its own weight. That's why the bow section has that distinctive slope, and they reinforce it with extra layers of steel. In some spots, the thickness multiplies several times over, and inside they add ribs that distribute the load along the entire length of the ship. While I'm walking around here, there's constant movement everywhere. Cranes, platforms, people in hard hats, for whom all this is just another workday. Though honestly, when they're moving a whole section weighing dozens of tons right over your head, you kind of rethink the word ordinary. One of the engineers jokes that the scariest thing here isn't the cold or the metal, it's when someone forgets their lunch in the shop, because finding it among all this scale is practically impossible. When all the sections are connected, the hull starts taking its final shape. Its length becomes physically tangible. You walk alongside and catch yourself thinking it's like strolling past an apartment building, only horizontal. The height of the hull is impressive too. Several levels that will eventually become decks, engine rooms, and crew quarters. After that comes surface treatment. The metal gets cleaned, anti-corrosion coatings applied, painted with special compounds that reduce water friction and protect the hull from salt and ice. It looks like cosmetics for a giant, but in reality, this coating determines how many years the ship can operate without major repairs. And that's not an exaggeration. Arctic saltwater and constant ice friction can destroy unprotected metal in just a few seasons. Modern nuclear icebreakers can ram through ice up to 9 feet thick while underway, and the newest designs are rated for ice up to nearly 15 feet thick. Power, that's a whole other story. Heavy icebreakers can pump out over 75,000 horsepower, and without that, they simply wouldn't budge the ice. I'm standing here staring at this hull, and it hits me. This isn't a finished vessel yet. There's no reactor in here, no propellers, no control systems. But even now, the main thing is crystal clear. This is a structure built to battle the elements, where every millimeter of steel serves a purpose. And when she heads out to sea, she won't just sail. She'll carve a path where other ships wouldn't even dare to go. I'm gonna stick around here a bit longer. Listen to that metal grinding. Watch these machines come to life. Then head out to prep your next adventure. Because after something like this, you want to find something just as massive, just as complex, just as beautifully insane. When you stand next to a structure like this, you start seeing what humans can actually build differently. Not on a computer, not in theory, but right here, with hands, steel, and fire. And I think I've already got a couple ideas where to head next, so stick around. It's gonna be good.
Every second, the world transmits over 3 billion gigabytes of data. But do you know that all of this is thanks to a thread thinner than a human hair? And that this thread begins with ordinary sand? Not beach sand, but perfectly pure quartz, where there's only one impurity particle per million particles. To create fiber optic cable that carries light at speeds exceeding 300,000 kilometers per second, you need to journey through chemical vapors, sterile laboratories, a furnace at 2,500 degrees, and lasers that monitor every microcrack. This process looks more like manufacturing a spacecraft than a cable. But it's precisely this that forms the foundation of the internet you're using right now. To create a thread capable of transmitting light at speeds approaching 300,000 kilometers per second, you must begin with sand. But not just any sand, only special, exceptionally pure quartz sand, where the primary substance is silicon dioxide. For fiber optic production, sand with a silica content exceeding 99.9% is used, which means that in 1 million particles, only one particle is an impurity. Just imagine, in every kilogram of raw material, no more than a few milligrams of impurities. And this is critically important, because even a tiny particle of foreign metal can cause light scattering or absorption. And then a signal that should have traveled nearly 100 kilometers without amplification simply vanishes. Raw material for fiber optics isn't simply washed or filtered, it's purified at the molecular level. Manufacturers often employ gas chemistry. Quartz sand is converted into gaseous silicon tetrachloride, which is then distilled, filtered, and precipitated as the purest vapor. And only then is it converted back into glass. Add to this strict temperature control, humidity, and airflow in clean rooms, and you'll get an idea of how far removed this is from an ordinary sandy beach. Production laboratories resemble NASA's sterile zones more than a glass workshop. And all of this to ensure that every meter of future fiber contains not a single defect. A large transparent glass cylinder, which will later be melted and drawn into an extremely thin thread, is the fiber optic preform. This enormous glass blank is made using a method called vapor deposition. In a large furnace, air is mixed with extremely pure gases. These vapors reach the inner surface of a transparent tube that's heated intensely. When the vapors touch the hot wall, they settle and transform into tiny glass droplets, like dew collecting on a leaf in the morning. Gradually, these droplets accumulate layer by layer until a thick layer of glass forms inside the tube. Then this tube is heated even more intensely, and it closes into a dense solid rod. This is our preform. The preform is placed in a special furnace where the temperature reaches approximately 2,600 degrees Celsius. This temperature is so high that the glass becomes soft and begins to melt, like caramel on a hob. When the preform's end melts, a drop of molten glass begins to drip from it. This drop is very carefully drawn downwards, and from it forms the finest thread. This thread, the optical fiber, is drawn at speeds of roughly 300 meters per minute. Imagine, that's faster than a cyclist moving through the city. It's important that the thread has the same thickness along its entire length. Optical fiber thickness is typically around 125 microns. This is very, very thin. For comparison, the average human hair has a thickness of around 100 microns. To keep this diameter under control, special instruments are positioned in the process. They monitor the thread in real time and measure its thickness. If the thread begins to become thicker or thinner, the system automatically changes the drawing speed or furnace temperature to correct it. After the optical fiber has been drawn and has become a thin, transparent thread, it needs protection. The fiber is extremely thin and fragile. Therefore, immediately after drawing, it's coated with a special protective layer. The thin thread is drawn from the furnace. After the furnace, it immediately enters a coating machine, a special device that dresses the thread in a plastic sheath. The optical fiber enters a special part of the machine called the coating head. This resembles a small tube or nozzle, inside which sits molten protective material. As the fiber passes through this tube, a layer of liquid polymer is evenly poured onto it. This coating layer typically consists of two parts. The primary coating is a very soft, elastic layer that dampens mechanical shocks. The secondary coating is harder and stronger, protecting from external influences, dust, and scratches. After applying the liquid coating, the fiber passes through special forming rollers. They regulate the layer's thickness and evenness. After the polymer has been applied and formed, the fiber passes through an ultraviolet light zone. Here, under UV lamp influence, the polymer instantly hardens. This process is called polymerization. Those of you who get manicures know how this works. Ultraviolet lamps activate chemical reactions in the polymer. Thanks to this, the coating quickly becomes hard whilst maintaining its elasticity. This is an extremely rapid process. The coating hardens literally in fractions of a second. This method doesn't heat the fiber so it doesn't damage it. The entire machine is equipped with sensors and control systems. They constantly measure coating thickness and fiber feed speed. At the end of all this technological wizardry sits a spool module, rotating with a hum resembling a jet engine sound in miniature. The fiber, resembling transparent silk, lays evenly and precisely coil against coil. The spool moves smoothly left and right with millimeter precision. Around it are sensors, lasers, cameras. They vigilantly monitor that the fiber lays evenly and doesn't twist. With every minute, more and more layers appear on the spool. Imagine, in just a few hours, there are already several kilometers of the finest, almost invisible fiber. And all of this without a single break, without a single scratch. Before assembly into cable begins, fiber from the spool is carefully rewound onto the production line. Since one cable typically contains several fibers, individual threads are combined into ribbons or modules. These ribbons or bundles are then placed into buffer tubes. These are thin, flexible plastic channels that provide the fiber space for micro-movements. This is important because when temperature changes or the cable bends, the fiber slightly expands or contracts. Inside these tubes, gel may also be added that repels water and absorbs vibrations. Around the buffer tubes, reinforcing elements are added. Fiberglass or Kevlar. These are extremely strong threads that protect the cable from stretching. Metal wire is needed for additional mechanical strength. The central rod is a rigid element at the center that maintains the cable's shape. All of this is wrapped with an outer sheath. This is a dense plastic or polyethylene tube resistant to ultraviolet light, moisture, rodents, and temperature fluctuations. The cable is tested. Each fiber's transmission capacity is checked, along with bending strength and moisture resistance. Then it's wound onto large drums, marked, technical documents are added, and it's ready for transport and installation.
Imagine if construction could be not just strong, but ultra-lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in saltwater. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation, a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal.
Every year, humanity forges colossal anchor chains capable of withstanding a force of over 1,500 tons, enough to hold back an entire freight train loaded with coal. A single link can weigh more than 500 kilograms and be as thick as a tree trunk. But how is such immense strength born from a simple bar of red-hot steel? What brutal trials must every meter of this steel serpent endure before it is trusted to the depths of the ocean? Stay with us until the end to witness a process of fire, sparks, and true engineering alchemy. It all begins not in the forge, but at a steel mill, where a special alloyed steel is created from ore and scrap. This is no ordinary metal. To produce chains that can handle loads of thousands of tons, you need the highest grade of steel, one capable of resisting not only tension, but also the embrittlement that comes from the extreme cold of Arctic waters. After smelting and chemical analysis, the steel is cast into massive cylindrical billets. These billets, while still hot, are passed through rolling mills that, with incredible force, squeeze and stretch the metal, forming it into long, round steel bars with a diameter that can exceed 200 millimeters.
The production hall is a kingdom of fire and metal. The air here is thick with the hum of machinery and the sharp, distinct smell of incandescent steel. It is here that the magic happens, transforming a straight bar into a curved, closed loop. First, the steel bar enters the infernal mouth of an induction furnace. In a matter of minutes, a powerful electromagnetic field heats it to 1200 degrees Celsius, making the metal plastic and malleable. The glowing bar is then immediately fed to a bending press. Hydraulic arms effortlessly bend it into its characteristic U-shape. Now comes the critical moment. While still hot, the U-shaped piece is threaded through the last, already completed link of the growing chain.
This is how the links are interconnected. The two ends of the U-shaped piece are then brought together and clamped tightly in the giant copper jaws of a welding machine. The process of flash butt welding begins. An enormous electrical current is passed through the joint. The metal at the point of contact instantly melts, accompanied by a blinding flash and a fountain of sparks. At that exact moment, a hydraulic press with hundreds of tons of force squeezes the molten pans together, fusing them at a molecular level into a single seamless piece. The excess metal, known as flash, is immediately sheared off by special cutters. While the link is still hot from welding, a special stud is fitted into its center. This crosspiece not only gives the link additional rigidity, but, most importantly, prevents it from deforming and tangling during use. After the stud is set, the entire chain, or a section of it, undergoes heat treatment. It is reheated to a precise temperature and then rapidly cooled or quenched in a huge pool of water. This process makes the steel extremely hard, but also brittle. To remove this brittleness, the chain is heated again to a lower temperature and left to cool slowly in the air. This final step is called tempering. Not a single meter of a giant chain leaves the factory without undergoing a series of the most stringent tests. This is the guarantee that it will not fail at a critical moment. First, the entire chain is subjected to a proof load test. It is secured in a special testing machine, a colossal hydraulic bench dozens of meters long. The machine begins to stretch the chain with a force significantly greater than its nominal working load. Inspectors meticulously examine every link for any sign of deformation. But the most dramatic trial is the break test. A test sample of several links is cut from the finished batch. It is placed in the same machine and pulled until it shatters. The deafening crack of rupturing metal is not a sign of failure, but the ultimate confirmation of the entire batch's quality. After the mechanical tests, every single link is inspected with ultrasound to detect any hidden internal flaws. Only after successfully passing all these stages does the chain receive its quality certification. Loaded for transport, it looks like a sleeping steel leviathan ready to begin its silent service in the depths of the ocean. For the highest grade chains, this proof load can exceed 1,000 tons. This means the chain is stretched with a force equivalent to the weight of 3 Boeing 747s. The minimum braking load for such products often exceeds 1,500 tons. Behind every giant link is a world of impressive numbers. A single link of a top-grade anchor chain can be forged from a steel bar over 200 millimeters in diameter. The weight of such a link easily exceeds 500 kilograms, more than a grand piano. However, chains are not measured by the link, but in sections. A standard marine section, or shot, is 27.5 meters long. The complete anchor chain for a supertanker can consist of 12 to 15 of these shots, reaching a total length of over 400 meters. Its total weight can easily exceed 250 tons, comparable to the weight of 2 adult blue whales. Every year, more than 50,000 tons of uranium are mined across the globe. But to extract just a few grams of its energy, mountains of rock must be moved. It's a journey that begins in a desert where the temperature hits 38 degrees Celsius and ends inside a reactor that powers New York City. It involves centrifuges that spin faster than a jet turbine and chemicals that can dissolve metal in seconds. But the most interesting part is something that even the safety manuals don't mention. Watch until the end and you will learn a secret that will change how you think about nuclear power forever. It all begins in the dust, literally. Uranium ore is mined in hot, arid regions: Arizona, Wyoming, Texas, New Mexico. Here, the sun is relentless, reaching 38 degrees Celsius in the shade, if you can find any. There are two main extraction methods: open pit mining, where the topsoil is stripped away, and underground mining, with explosives and hoists. There is also a third, more subtle technique: in situ leaching. Pipes are drilled deep into the earth. Special solutions are pumped down to dissolve the uranium directly from the rock, and the resulting liquid is then pumped back to the surface. The ore itself, a grayish-brown rock, looks unremarkable, but within it, the crucial isotope uranium-235 makes up just 0.7%. The rest is a vast, almost useless mass that is inert in a reactor. And to squeeze the required drop of energy from it, hundreds of tons must be processed. After mining, the ore is crushed, milled into a fine powder, and thrown into a chemical bath of acid or alkaline solutions. This is followed by filtration, precipitation, and drying at 260 degrees. The final product is yellowcake, a bright yellow uranium concentrate. Officially, it's known as uranium ore concentrate, but everyone at the plant just calls it yellowcake. It looks striking, a mustard-colored loose powder like a spice for a barbecue. But this is a substance you must not touch and must never inhale. It emits alpha radiation, has a long half-life, and its dust is dangerously toxic. The yellowcake is sealed in double-walled drums, loaded onto escorted trailers, and plastered with radiation warning signs for the journey to the enrichment facility. This is the start of the path that turns a poisonous dust into the clean white light from a lamp over your kitchen table, or the electricity that powers the tube deep beneath London. Right, the yellowcake has arrived. It's radioactive, dry, and sealed in its drum. The next step? Turn it into a gas. And not just any gas. This is uranium hexafluoride. The uranium concentrate is first dissolved in acid, purified, and converted into uranium dioxide. And here, the alchemy begins. The uranium dioxide is treated with fluorine gas in special reactors at 540 degrees. The reaction creates a volatile, transparent gas that boils at just 56 degrees. A little heat, and it turns from solid crystals into a vapor. But it's not that simple. This gas is extraordinarily toxic. It corrodes most metals, destroys human tissue, and on contact with humid air, it instantly transforms into hydrofluoric acid and uranyl fluoride, a lethal cocktail. That is why this entire process is conducted inside sealed, automated reactors. The substance is stored as solid, whitish crystals, formed by cooling it to room temperature. These crystals are kept in steel cylinders, each engraved with a serial number and a radioactive symbol. A single cylinder weighs almost 14 tons. You think your washing machine spins fast? You haven't seen a nuclear centrifuge. They can reach 70,000 revolutions per minute, more than 10 times faster than a jet engine turbine. And all for one purpose, to separate uranium isotopes. Uranium hexafluoride, that toxic gas we just created, is fed into a tall, narrow cylindrical chamber, which is then spun at an insane speed. Centrifugal force does the work. The heavier uranium-238 atoms are flung towards the outer wall, while the lighter, crucial uranium-235 atoms remain closer to the center. But one centrifuge isn't enough. They are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas and passes it to the next. This process is repeated, cycle after cycle, until the concentration of uranium-235 reaches at least 3 to 5%. This is the standard grade for reactor fuel. Okay, the gas is enriched, but you can't feed a reactor with the gas. So now it is converted back into a solid, this time a ceramic form. After a series of chemical reactions, the gas becomes uranium dioxide powder, a dark gray solid. This powder is pressed under 20 tons of pressure into small cylindrical pellets, just 8 millimeters in diameter. They look almost harmless. Next, the pellets are sintered in a furnace at nearly 1650 degrees, making them as hard as porcelain. They are then polished and ground to precise dimensions. The finished pellets are loaded into long metal tubes known as fuel rods, typically made of a zirconium alloy because it resists corrosion and can withstand intense radiation. Each rod holds over 300 pellets. The rods are hermetically sealed and then bundled together into modules called fuel assemblies. They look like a square frame holding a grid of several dozen rods. A single assembly can weigh over 680 kilograms and will operate inside a reactor for up to 6 years. The finished fuel is packed into armored containers for transport. The journey is made under guard, on a special route with a security escort and GPS tracking. Left over from all of this is the depleted uranium hexafluoride, known as tails. It's a mix of isotopes with a small amount of U-235 remaining, but not enough to be useful. These tails are stored in steel cylinders at designated secure sites. When a fuel assembly has served its 4 to 6 years in the heart of the reactor, it is no longer a shining star. It is removed by a robotic system and moved into a deep pool of water, over 6 meters deep. The water cools the assembly and shields the intense radiation because the fuel is still incredibly hot. It rests there for several years. After that, it has 2 possible futures: long-term dry storage in concrete and steel casks, or reprocessing. This usually happens in other countries, as the US and UK primarily store their waste rather than reprocess it. In a dry storage facility, the assemblies stand for decades, cooled by natural air convection, as if in a nuclear monastery. This isn't the end, but a new phase of life. A slow, controlled existence, but one deeply connected to the future of energy. Because even after its time in a reactor, this fuel remains a source of heat, a lesson in engineering, and a reason for profound respect.
Have you ever seen what molten bronze looks like? I have. It's golden, almost like the sun, and flows slower than water, thick, heavy, with this inner weightiness to it. And when 70 tons of this metal get poured into a single mold all at once, it's a sight you can't look away from. Today we're at a factory that makes propellers for military ships. This is one of those places they don't run tours through and almost never film inside. And I'm going to show you the entire journey from molten bronze to a polished giant that will silently push thousands of tons of steel through the ocean. Let's start with a question I asked myself when I got here. Why bronze? A warship is a steel machine. Steel hull, steel superstructure, steel weapons. So why make the propeller from a different material? The answer is simple yet profound. Steel rusts in seawater. The propeller is constantly submerged, constantly spinning, constantly in contact with an aggressive environment. A steel propeller would turn into a rusty hedgehog in just a few years, one that can't do its job anymore. That's why they use nickel aluminum bronze here, an alloy that sailors and metallurgists call nibral for short. Nibral is a mix of copper, aluminum, nickel, and iron in precisely calibrated proportions. Copper provides the base and corrosion resistance. Aluminum strengthens the alloy and reduces weight. Nickel adds hardness and erosion resistance, and iron refines the grain structure, making the metal uniform. Every element here is deliberate, the result of decades of research and real-world testing.
Nibral doesn't rust, resists erosion incredibly well, and has enough strength to handle the loads from spinning at full speed underwater. Now, about scale. A propeller for a destroyer or nuclear submarine, this isn't something you can pick up with your hands. The diameter of such a propeller reaches 20 feet or more, and each blade is comparable in size to a small car. The weight of the finished product, dozens of tons. And it all starts with 70 tons of liquid bronze that needs to be poured into a single mold in one continuous process. 70 tons. That's roughly the weight of 12 fully loaded pickup trucks. And all this massive metal at a temperature of around 2,000 degrees Fahrenheit has to get into the mold evenly, no pauses, no stops. The metal is melted in large induction or arc furnaces. Depending on the plant's configuration, there might be several of these furnaces, and they run in parallel to accumulate the necessary volume of molten metal by the time of pouring. When the metal hits the right temperature, lab techs take a sample, a small portion of the melt, and send it for rapid chemical analysis. If the element ratios check out, they greenlight the pour. If something's off, they adjust it right there in the furnace, adding whatever element is needed, then take another sample. The pour happens from a big ladle suspended from an overhead crane. They tilt the ladle, and metal starts flowing into the gating system of the mold. It looks like this, a thick golden stream with bright glow and a cloud of steam rising up. The air shimmers from the heat, and 30 feet away you can feel the hot wave hit your face. The foundry workers stand off to the side in protective suits and shields. Even several yards out, the heat hits your whole body. They control pour temperature by adjusting the ladle tilt. Too fast, and the metal churns turbulently in the mold, trapping air and creating voids. Too slow, and the first portion starts solidifying before the mold fills, leaving internal seams in the casting. So the pace stays steady, continuous, dialed in by experience. When the mold is complete, they leave what's called a riser at the top, an extra reservoir of metal that feeds the casting as it shrinks during cooling. Without it, shrinkage cavities form inside the propeller, voids that would render the blade useless. The riser gets cut off later, but during the pour, it's a critical part of the process. The mold for a propeller is a massive structure that takes up a significant portion of the foundry floor. It's assembled over weeks from special molding sand reinforced with binding resins. Each blade has its own complex geometry, twisted, uneven, with a precisely calculated profile. This geometry is built into the sand mold with high precision. The raw casting already needs to be very close to the final part. Worth noting separately are the cores. Cavities are designed inside the blades to reduce weight without sacrificing strength. To form them, sand cores are mounted in the mold on metal supports called chaplets. During the pour, the chaplets fuse with the base metal and become part of it, while the cores are later knocked out of the finished casting. Sounds simple, but in practice,
It's precision work, carefully controlling the position of every rod. If a rod shifts under the weight of molten metal during the pour, the blade wall comes out uneven. An uneven wall means imbalance. Imbalance on a submarine propeller means vibration. Vibration means noise. And noise underwater? That's a death sentence for a sub, because enemy hydrophones will pick it up. This brings us to the main theme of this facility: silence. A warship, and especially a submarine, must be as quiet as possible. The propeller is the primary source of underwater noise. There are two mechanisms: mechanical noise from imbalance and vibration, and cavitation noise. Cavitation is a phenomenon where microscopic vapor bubbles form on the blade surface due to pressure differences, then collapse with a distinctive crackle. Each pop is a micro-impact that, over time, destroys even bronze, leaving small pits on the surface. But the main problem isn't wear, it's sound. That crackling travels brilliantly through water and is easily detected by sonar systems. That's why blade surfaces must be perfect: no roughness, no waviness, no deviations from the calculated profile. That's exactly why there's a 5-axis CNC milling machine standing here. If you've never seen one of these machines, picture something between an industrial robot and a building. The work envelope can handle parts up to 20 feet in diameter. The spindle and cutter move simultaneously along 5 axes, 3 linear and 2 rotational. This lets the tool approach any point on a complexly twisted blade at exactly the right angle and remove metal with micron-level precision. The price tag on one of these machines? A small fortune. But without it, achieving the required surface quality on parts this size is simply impossible. Machining a single propeller takes several weeks. Weeks, not hours. The machine strips away chips continuously, layer by layer, closing in on the final profile. Bronze shavings curl into golden spirals and drop into the catch pan, while beneath the cutter emerges a surface smooth as glass. Operators regularly pause the process to measure blade geometry using specialized probes and laser scanners. Any deviation from the theoretical profile? The program gets adjusted. The goal is to achieve a surface that matches the blueprint to within hundredths of a millimeter on a part that's 20 feet across. That's like drawing a perfect room-size circle without deviating from the line by more than the thickness of a sheet of paper. After machining comes balancing. The propeller gets mounted on a balancing stand and spun. Sensors detect exactly where the imbalance is and how much. Technicians manually remove metal from specific spots, literally just a few grams at a time, until the propeller reaches the required balance level. The process is painstaking. Shave off a tiny bit, measure. Shave again, measure again. Over and over until the sensors show it's within spec. On a civilian ship, this level of precision would be considered excellent. On a military vessel, it's the minimum acceptable standard. The final inspection includes complete measurement of every blade, surface roughness checks, and verification of the metal's chemical composition using samples taken during the melt. Each propeller gets a full documentation package, from the melt's chemical analysis to balancing protocols and laser surface scanning reports. This isn't just paperwork. It's a legal and technical passport for a product that'll go on a warship and serve for decades under the harshest operating conditions. I stood next to a finished propeller before shipping, trying to wrap my head around the fact that I was looking at something that had gone from liquid bronze to this golden, polished giant in just a few months, through the work of dozens of people and one very large machine. Somewhere out in the ocean, this propeller will spin in complete darkness, pushing thousands of tons of steel forward. And it'll do it silently. Because that's exactly what it was built to do.
Every year, people around the world devour over 50 billion pieces of fried chicken, millions of burgers, and 1 billion pizzas. But hardly anyone stops to think about what's behind those perfectly golden crusts and aromas we've come to take for granted.
What if I told you that inside these flavor factories, technologies operate with more precision than surgical instruments, and recipes are guarded more closely than military secrets? In this video, you'll see how the food the entire planet loves is made, from KFC's secret blend of 11 herbs and spices to Domino's billion pizza assembly line. Stick around until the end, and you'll learn things they've never revealed, even in their advertising. Do you love KFC fried chicken as much as I do? Its story doesn't start in a fryer, but on massive American farms where chickens are raised under the strictest safety standards. After arriving at the plant, each bird flows through a cascade of automated systems. Artificial intelligence, like a vigilant guardian, analyzes images from high-resolution cameras, filtering out any defects. This isn't just a conveyor belt. This is a river of raw material flowing through an incredibly complex control system. Only the best specimens, passing this digital selection, move to the next stage. This is the first level of guarantee that every single piece will be perfect.
What follows is a processing stage that resembles a high-tech ballet. The carcasses are plunged into water at a precisely calibrated temperature of 140 degrees Fahrenheit to soften the feathers. Then, automated machines equipped with thousands of rubber fingers spinning at tremendous speed strip away the plumage in seconds. These units can process up to 10,000 carcasses per hour. After that, laser-guided robotic cutters divide the carcasses into 9 standard parts with surgical precision. No more, no less. Every single piece gets weighed, scanned, and assigned its own digital footprint in the production management system.
But here's where things get really interesting. The chicken gets marinated in a special brine that makes the meat incredibly juicy. And then comes the sacred ritual, the breading. That legendary secret blend of 11 herbs and spices, a recipe Colonel Sanders developed way back in 1940, remains one of the most closely guarded trade secrets in the world. Where it is, the original recipe sits in a vault at KFC headquarters. The blend ships to factories in 2 separate bags, and they only mix the contents right before breading. The breaded chicken gets fried in special pressure fryers at 375 degrees. It's that pressure that locks in the juiciness inside while creating that iconic crispy coating outside.
If beef's more your style, welcome to the world of the Big Mac. McDonald's uses only 100% beef from verified suppliers. After rigorous inspection, the meat's ground and formed into patties weighing exactly 1.6 ounces. This precision isn't a quirk, it's what guarantees each patty cooks perfectly. To preserve freshness without preservatives, the patties undergo flash freezing at 0 degrees Fahrenheit. This allows ice crystals to form instantly without damaging the meat structure. Big Mac buns are baked on automated lines, where the dough is mixed, shaped, and topped with exactly the amount of sesame seeds the standard requires. Vegetables, crispy iceberg lettuce, onions, pickles, go through multiple rounds of washing and slicing. But the real secret of the Big Mac? That's the sauce. Its exact recipe is another mystery, guarded like classified intel. In restaurants, frozen patties get seared on a double-sided grill at 425 degrees for just 42 seconds. That's the perfect window. Golden crest on the outside, juicy meat inside. Then the crew, like soldiers on an assembly line, stacks the burger in strict order in mere seconds. That's why this icon of an era has stayed exactly the same for over 50 years.
Did you know the Domino's pizza story started with a $500 debt? In 1962, two brothers bought a small pizzeria in the American town of Ypsilanti. Their main promise, which became the driving force of the entire industry, pizza delivery in 30 minutes. This rule sparked a revolution. Today, everything starts with the dough. At giant facilities, flour, water, yeast, and oil get mixed in industrial mixers. The dough rises in chambers with controlled humidity and temperature. Then it's divided into portions, shaped into round bases using presses, and flash frozen. That's what makes it possible to deliver identical dough to thousands of pizzerias around the world.
Tomato sauce is made from specially grown tomato varieties that get processed into puree within hours of harvest. Mozzarella is shredded on industrial graters, and pepperoni is sliced with laser precision. Sauce gets spread on the base, cheese is sprinkled on top, and exactly the number of pepperoni slices required by the standard gets laid out. Then the pizza heads into a conveyor oven at around 500 degrees Fahrenheit. Domino's Pizza is the world's largest pizza chain, cranking out roughly 1 billion pizzas every year. Their newest automated dough production center in Indiana can produce enough raw dough for tens of thousands of pizzas daily.
But how does all this food produced in giant factories make it to our table while staying fresh and flavorful? Behind it lies an invisible yet incredibly complex system, cold chain logistics. It's the actual nervous system of the global fast food empire. Frozen patties for the Big Mac and chicken for KFC travel in special refrigerated trucks where the temperature is maintained at -4 degrees Fahrenheit, accurate to within a degree. Sensors transmit temperature data to a central server in real time. Any deviation, the system sounds the alarm. Buns, vegetables, and sauces are transported in separate compartments at their own optimal temperatures. It's a whole science ensuring products don't thaw and refreeze, which destroys their texture and flavor.
Why does a Big Mac in Tokyo taste exactly like one in New York? The secret lies in sensory analysis science and obsessive consistency. Every major company has what are called sensory panels, teams of specially trained tasters with superhuman taste and smell. Their job? Sample products and compare them against the gold standard, a reference sample stored in the lab. They evaluate dozens of parameters: the saltiness of the sauce, the crunch of the lettuce, the softness of the bun, the aroma of the patty. Any deviation from the standard, even the slightest, and the entire batch can be rejected. It's a genuine flavor DNA code that companies replicate and reproduce worldwide. So no matter where you are, you always get that same familiar taste from childhood.
So what's the main secret promised at the start? It's not 11 herbs and spices, and it's not some sauce recipe. The real secret these giants are hiding is creating consistency. It's psychology. The secret is they're not just selling food, they're selling comfort. In a world full of uncertainty, you always know exactly what your Big Mac or chicken wing will taste like. This isn't just lunch, it's an anchor of stability, a flavor that hasn't changed in years and decades. They took the most complex processes, from animal genetics to global logistics to flavor chemistry, and packaged them in a simple cardboard box. And they made us believe it's simple, fast, and always tastes the same. And that's their real genius.
$1,300,000,000 meters of submarine internet cables have already been laid on the ocean floors. And every year, this length grows. Also, we can send a message, watch a video, or make a call across continents. Over 95% of all intercontinental internet traffic passes through them every day. Stretched through the depths, they cross volcanic ridges, encounter sharks, ships, and even geopolitics. How are these gigantic infrastructures created? Who designs the routes? How are they laid on the seabed at depths of over 26,000 feet? And what happens when a cable is damaged?
For the internet to cross oceans, a cable is needed that can withstand pressure, salt water, marine life, and decades of operation without repair. It all starts with the central core, a copper or aluminum conductor, through which the main signal travels. Large ingots of purified metal are melted and passed through drawing machines, which repeatedly pull the material through narrowing dies, reducing the diameter to a few millimeters. At this stage, a perfectly round cross-section is formed, one that has no microcracks or air pockets. After drawing, the wire undergoes heat treatment. It is heated to a precisely set temperature to relieve internal stress and make it more flexible. Then it is cleaned of oxides, often by a chemical method, or using abrasive rollers.
The output is a shiny, smooth, almost flawless wire. It is checked automatically for diameter, resistance, flexibility, and surface purity. The wire must withstand kilometers of bending and work without failure, even at depths of several thousand feet. Depending on the type of cable, the wire is either used as a single solid conductor or is twisted from several thinner strands, which increases flexibility and protection against breakage. Once the copper or aluminum conductor is ready, it is immediately fed into an extrusion line, a long machine resembling a tunnel. Inside, polyethylene heated to 482 degrees Fahrenheit, which melts into a thick, viscous cream. The conductor moves along a conveyor and enters the extruder head, where the molten polymer precisely and evenly flows around the metal, like a second body. Every millisecond is important here. Too slow, and drips will form. Too fast, the polyethylene won't have time to adhere. Immediately after this, the cable enters a bath of cooling water, where the polyethylene layer quickly solidifies, tightly enveloping the conductor. The entire surface must be smooth, without a single bubble or crack. This is the first line of defense against moisture. After cooling, inspection. Lasers measure the insulation thickness, and cameras check the surface. If anything is even slightly off, the cable is cut and reprocessed. The next stage is the application of a hydrophobic gel, which acts as an invisible protector. This thick, viscous compound fills all the voids inside the cable, envelops the optical fibers, and creates an internal shield against moisture. In a special chamber, the cable passes through a system of nozzles or rotating heads that evenly apply the gel to the central part and in the space between the fiber elements. The gel resembles a transparent lubricant. It doesn't dry out, freeze, or dissolve in water, even at a depth of 26,000 feet under a pressure of hundreds of atmospheres. Its main property is to repel water. If the cable sheath is ever breached, the gel instantly spreads and prevents moisture from penetrating inside, not letting it reach the sensitive fibers. At this stage, it's also important that there isn't too much gel, otherwise it complicates the further laying of layers, and not too little. Then the protection efficiency drops. Computers precisely regulate the dosage, and operators visually check the filling and uniformity. After application, a short cooling and stabilization. Now the cable is ready to receive its optical heart, the fiber threads that transmit light from one continent to another. These fibers, usually from 4 to 12 of them, are first grouped into modules. Each module is a flexible capsule with several fibers inside, providing additional protection. The modules are very carefully arranged in a spiral around the central conductor. This configuration allows the fibers to bend without tension, especially during winding and laying the cable at sea. To keep the fibers in place, they are fixed in a bedding of gel that was applied earlier. There is no glue, only a tight fit and a flexible structure. It's important that no fiber crosses another, breaks, or shifts from its place.
The work is almost like jewelry making, although it's done on a conveyor. Afterward, a continuity check of each fiber. A laser beam is sent through them. Even a microcrack or a bend will cause a failure, and the fiber won't pass inspection. If everything is fine, the structure moves on to the next stage, additional insulation and reinforcement. First, an additional polymer layer is applied over the optical fiber structure. Often it's high-density polyethylene, or another flexible waterproof material. It protects against mechanical damage, friction, and moisture. This is again done in an extruder, similar to the one where the first insulation layer was applied. The cable passes through molten polymer and immediately enters a cooling bath.
After cooling, the cable enters the steel wire braiding section. Machines evenly lay steel rods or tapes in a spiral around the already insulated core. In shallow water areas, this armor is thicker to protect against anchors, fishing nets, and shark teeth. At depth, the armor is thinner or absent altogether. After reinforcement, another outer polymer sheath may be added, which seals the entire structure. Operators carefully inspect the cable surface, checking for uniform thickness, no abrasions, burrs, cracks, or armor misalignments. Then, automated tests. Lasers scan the thickness. Cameras capture every millimeter. Light pulses are sent through the fibers again. The signal must pass without delays or losses. If a defect is found at this stage, it is cut out and both ends are joined using a special technology, creating a sealed splice joint.
After inspection, the cable enters the marking section. Here, information about the batch, production date, cable type, and its purpose is printed on the outer sheath. Often, every few feet, so it's easy to identify the cable even during laying on the seabed. And finally, winding onto spools. These are giant drums with a diameter of up to 13 or 16 feet, which can hold up to 8,200 feet of cable. Each turn must lie flat, without twists, and with uniform tension. Automatic systems regulate the speed and tension force, and operators monitor each stage. If the cable is intended for installation at sea, the drums are immediately sent to ships, where they are installed on the deck. If not, they're stored in special warehouses with humidity control, because even minor corrosion can be fatal.
What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, then gets reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore flare up like tiny controlled earthquakes. Zinc, the fourth most consumed metal in the world after iron, aluminum, and copper. 12 to 13 million tons of zinc are produced every year. 60% of all zinc goes into galvanizing steel. Without it, bridges, cars, and buildings would rust many times faster. But here's the shocker. At 2,700 degrees Fahrenheit, zinc literally turns into vapor and disappears into the air, and then condenses back into liquid metal. In this video, you'll learn things you never suspected, and at the end, the main secret will be revealed that will forever change how you think about zinc.
Picture a massive underground mine somewhere in China, Australia, or Peru, the world's biggest zinc producers. These are entire underground cities stretching hundreds of feet, sometimes even miles beneath the Earth's surface. We're not talking about simple holes in the ground. This is a network of tunnels, shafts, ventilation systems, and lift shafts. Powerful drilling rigs bore holes into the rock, blast holes. Explosives get packed into these holes. After a carefully controlled blast, massive volumes of rock break apart. It's like a spectacular but controlled earthquake in miniature. Dusty air gets quickly cleared by powerful ventilation systems, which also pump fresh air down to these depths. The broken ore then gets loaded onto massive underground trucks or conveyor belts using front-end loaders. It's a genuine underground transportation flow, continuously moving, hauling tons of ore to the central lift shafts. From there, the ore rises to the surface using powerful elevators or specialized conveyor systems, climbing hundreds of feet straight up.
At every stage, from drilling to hoisting, strict safety protocols are followed because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock, containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a concentrator plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore into crushers that, with a deafening roar, break them down into smaller pieces. Then this crushed ore moves into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore is ground down to an extremely fine powder, almost like flour. This is critically important to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder is mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. The zinc mineral particles latch onto these bubbles and rise to the surface, forming foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can contain up to 60% zinc. Since zinc is often found alongside lead, the processing plant may run multiple flotation cycles to separately extract zinc concentrate from lead concentrate. The zinc concentrate you end up with still isn't pure metal. It has to go through metallurgical processing to get metallic zinc. And now we enter the world of extreme temperatures. If the pyrometallurgical method is used, the zinc concentrate first undergoes roasting. The concentrate is heated in specialized furnaces at temperatures around 1800 degrees Fahrenheit.
This removes the sulfur, which is part of the sulfide ore, converting it into zinc oxide. The sulfur transforms into sulfur dioxide gas, which is captured and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable product. Next, the zinc oxide is mixed with coal and heated to even higher temperatures, over 2200 degrees Fahrenheit, sometimes even 2700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process occurs. The carbon strips oxygen away from the zinc oxide, freeing up pure metallic zinc. And this is where that incredible wow moment of vaporization happens. At these temperatures, the metallic zinc transitions into a gaseous state. It evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is significantly higher, zinc literally turns into vapor, which rises and gets collected in specialized condensers.
The vapor cools and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or granules. Now for the history. Zinc has been known to humanity for thousands of years, though it was only isolated as a distinct metal in the 16th century. Ancient civilizations used brass, an alloy of copper and zinc, without knowing it actually contains zinc. In India and China, people learned to smelt zinc as far back as the Middle Ages. But modern industrial zinc production only began in the 19th century with advances in smelting technology. The primary use of zinc, galvanizing steel. Around 60% of all zinc produced goes toward protecting steel from corrosion. Zinc coating on steel creates a sacrificial layer. The zinc oxidizes instead of the iron, protecting the structure. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a surge in resource demand.
15 to 20% of zinc goes into making alloys like brass and die casting alloys. These alloys end up in car parts, home appliances, toys, plumbing, and electronics. Another 10 to 15% becomes zinc oxide and other chemical compounds. Zinc oxide has crazy wide applications: sunscreens and cosmetics, paints, ceramics, rubber manufacturing, and even livestock feed supplements. Its antibacterial and protective properties make it a universal ingredient. The rest of the zinc gets used in batteries, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, because zinc is absolutely vital for the human immune system. As for prices, like most commodities, zinc prices swing with global supply and demand, economic cycles, and what's happening in the biggest producer and consumer countries. Yet demand for zinc remains steady or growing, driven by urbanization, infrastructure development, and the need to protect metals from corrosion worldwide. This makes zinc a crucial indicator of global economic health. Zinc ranks as the fourth most consumed metal on the planet, after iron, aluminum, and copper. That alone tells you just how massive its importance is for the global economy and industry. Annual worldwide zinc production sits at roughly 12 to 13 million metric tons. These are enormous volumes, underscoring its irreplaceability across hundreds of applications. The primary zinc mining regions are China, Australia, and Peru. These three countries together account for a significant share of global zinc ore extraction, making them key players in the market. For instance, China isn't just the largest producer, it's also the world's biggest zinc consumer, reflecting its powerful industrial expansion. Other major producers include India, the United States, Mexico, and Canada. When it comes to reserves, the U.S. Geological Survey estimates global zinc reserves at roughly 250 million metric tons. On top of that, there are what's called resource spaces, potential deposits that haven't been explored yet or aren't economically viable to mine right now. Those are estimated at over 1,800 million tons. These numbers show that zinc, unlike some rare metals, will last for many decades, even with growing consumption. Most zinc is mined from underground operations, entire subterranean cities stretching hundreds of feet, sometimes several miles beneath the Earth's surface. These aren't just holes in the ground, they're networks of tunnels, shafts, ventilation systems, and hoisting shafts. It all starts with exploration. Geologists, like detectives, hunt for ore bodies, sections of rock where the concentration of zinc, which, by the way, usually occurs as sulfide ore, like sphalerite, and almost always comes with lead, silver, and sometimes copper, is high enough to make it worthwhile. Once a deposit is discovered, mine construction begins. This involves sinking vertical shafts, which provide access to the ore, lift materials up, lower equipment down, and creating horizontal tunnels, or drifts, that lead directly to the ore veins. The actual ore extraction process? Dynamic, risky. Miners use specialized equipment, powerful drilling rigs that bore holes into the rock, called blast holes. Explosives get packed into these holes. After a carefully controlled detonation, massive volumes of rock shatter. It's like a spectacular earthquake, in miniature, under control. And that's how, starting from an underground explosion, through crushing into powder, through flotation with millions of tiny bubbles, through roasting at 1800 degrees and reduction at 2700 degrees, where the metal literally turns into vapor and vanishes into thin air, then condenses back into liquid zinc, a metal is born that shields steel from rust, makes bridges possible, cars, skyscrapers, without which the modern world would look completely different.
Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of two glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s, when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred: improvements to laminated glass, and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between 2 glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements. Thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable, and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment.
Every year, millions of tons of wood waste are generated worldwide, and most of it could simply vanish into landfills. But this is where a remarkable story begins, transforming ordinary wood chips, shavings, and even old furniture into solid boards that become the foundation of our everyday comfort. This isn't just manufacturing, it's a second life for timber. Picture mountains of raw material as tall as a 5-story building disappearing into steel monster machines only to emerge in a completely new form. And right now, we're about to reveal all the secrets of this process, which combines scale, precision, and a touch of engineering wizardry. It all starts at a massive raw material yard, where the foundation for future boards arrives in a continuous stream. Contrary to popular belief, high-quality timber is almost never used in their production. On the contrary, the manufacturing philosophy is all about giving wood waste a second life. Mountains of raw material are brought here, reaching heights of dozens of meters. The foundation is industrial wood chips obtained from low-grade timber. A huge proportion comes from sawmill waste, slab wood, offcuts, and thin battens. Wood processing waste is also heavily used, such as shavings and sawdust generated at furniture factories. A separate and important category is reclaimed timber. Old wooden pallets, crates, and even used furniture are given a chance at a new life as part of chipboard after thorough cleaning. Every batch of raw material undergoes strict incoming quality control. The first stage of cleaning is removing metal inclusions. Powerful electromagnetic separators screen the flow of raw material, extracting nails, staples, and any other metal fragments. The material then passes through screening systems to remove sand, stones, and other debris. If whole logs are used in production, say 20-foot lengths, they must pass through a debarking machine. Inside a massive rotating drum or using special cutters, the bark is stripped away. This step is critically important because bark has a different structure, contains loads of dirt, and significantly deteriorates bonding quality. The prepared and cleaned timber begins its journey along a conveyor belt hundreds of meters long, carrying it towards the first stage of mechanical transformation. It disappears into the steel jaws of a giant chipping machine, an industrial monster the size of a small room. Spinning at thousands of revolutions per minute, its blades bite into the timber with incredible ease, transforming solid pieces into a stream of uniform chips a few centimeters in size. But this material is only semi-finished. The resulting chips are too large and coarse. So the next step is finer, more precise secondary grinding, which takes place in specialized particle mills. It's here, amid the roar of high-precision equipment, that the actual wood particles are born, the ones that give the final product its name. At this stage, the geometry of the particles becomes absolutely crucial. For the outer, face layers of the board, which will be responsible for its appearance, very fine, thin, and flat particles are needed. These are produced in knife ring fakers, which literally slice thin flakes off the chips, resembling cornflakes. For the inner, core layer of the board, which forms its structural backbone, larger and thicker particles are used. This creates a strong internal framework that gives the board its final rigidity, bending strength, and the ability to reliably hold fixings such as screws and bolts. The resulting moisture mass has varying moisture content, which is unacceptable for quality bonding. So all the particles are sent to one of the most crucial stages, drying. Typically, huge drum dryers are used for this. Particles flow continuously into a rotating drum where they're blasted with hot air. The final moisture content of the particles must be within a very narrow range, from 2 to 6%. If the particles are over-dried, they won't absorb the adhesive properly. If they remain too moist, during hot pressing, excess steam can literally blow apart the board from within. Now comes the turn of the key component that will transform the loose mass of particles into a monolithic board, the binding agent. Most commonly, these are synthetic resins. The sorted particles enter special continuous action mixers. Inside them, resin is sprayed through nozzles, creating an adhesive mist that evenly coats every wood particle. Resin dosage is critically important and typically ranges from 6 to 10% of the dry particle mass. The resin-coated particles, now sticky and ready for bonding, are finally prepared to become board. They're transported to a massive forming machine where scattered particles give birth to a continuous particle mat. This is where the engineering magic of creating a 3-layer structure happens. The forming machine is a complex system that sequentially and with high precision deposits particles onto a moving conveyor belt. First, it creates a perfectly even bottom layer using the finest fraction. Immediately after this, a significantly thicker middle layer is laid onto this foundation, consisting of large and strong particles. Finally, the entire mat is covered with another layer of fine fraction, creating a mirror image of the bottom layer. This precisely calibrated structure, resembling a sandwich, provides unique properties to the future board. Its smooth and dense outer layers are ideal for subsequent sanding, whilst the strong internal layer gives the board its necessary rigidity. The formed but still loose mat passes through a prepress, where it's significantly compacted. This prepressing removes excess air and gives it a shape convenient for loading into the main press. This is the culmination of the entire technological process. The pre-pressed and cut mat sections are fed into the hot press. Inside the press, two powerful forces act simultaneously on the particle mass. Enormous pressure, reaching dozens of kilograms per square centimeter, compresses the particles. At the same time, the press plates, heated to 200 degrees Celsius, transfer their heat to the mat. This high temperature activates the resin, triggering an irreversible polymerization process. The liquid adhesive instantly transforms into an extremely hard and durable polymer, which permanently bonds millions of wood particles together. During this brief moment, the loose mat transforms into a hot, solid, and absolutely monolithic chipboard. Hot boards straight from the press can't be stacked immediately. They need to cool gradually to relieve internal thermal stresses. For this, they're placed in special star coolers, where they're ventilated for several hours. The next step is calibration and sanding. Boards pass through multi-head sanding machines, where wide abrasive belts remove a thin surface layer, bringing the board to its precise specified thickness and creating a perfectly smooth surface. At the final stage, large production boards are cut into standard commercial formats and their edges are trimmed. Finished products undergo strict quality control. Only quality boards are marked and sent to the warehouse. Every year in Dubai alone, over 1 million tons of asphalt are produced, and that number is constantly rising. Imagine it, tankers carrying millions of barrels of crude oil dock at Jebel Ali port. The oil is distilled in reactors at over 350 degrees Celsius, and a black, heavy residue is transformed into an advanced, elastic bitumen. Then come minerals from the mountains of Fujairah, processed at hundreds of tons per hour, blended in automated mixers, and transported in insulated trucks. This is the engineering magic that gives Dubai roads that neither melt in the sun nor crack in the night. Watch until the end, and you will discover the secret that makes this asphalt tougher than the desert itself. It all begins on the waters of the Persian Gulf, where giant tankers slowly cut through the surface, carrying millions of barrels of black gold, crude oil. They journey from Iraq, Saudi Arabia, and Kuwait. When a tanker docks at a port in the UAE, such as Jebel Ali, a process begins where men and machines work as a single organism. The oil is pumped into vast storage tanks, hidden within the industrial landscape, marking the start of its transformation. From there, it travels underground through a network of pipelines, like arteries leading to the heart of the refineries. In Jebel Ali or Abu Dhabi, it is met by a city of steel, reactors, distillation towers, and chrome columns. Here, the crude oil is heated to over 350 degrees Celsius to separate it into fractions. Lighter components, petrol, diesel, kerosene, vaporize first. The heaviest residues, the ones that refuse to vaporize even at these temperatures, are exactly what we need. This residue is fed into a vacuum distillation column, where the pressure is dropped to a minimum. What remains is bitumen, a black, viscous substance, the soul of asphalt. On its own, however, this bitumen is too thick and brittle for road construction, especially in a desert where the surface temperature can reach almost 50 degrees. So it must be modified. In special reactors, the bitumen is blended with polymer additives, plasticizers, stabilizers, and sometimes even crumb rubber. This is the bitumen modification process. The result is a material with high elasticity and resistance to UV radiation, one that won't soften under the sun or crack when the temperature plummets at night. In Dubai, a polymer-modified bitumen that meets the strict standards of the RTA, the Emirates Roads Agency, is used almost exclusively. Once the bitumen has completed its transformation, it begins the next stage of its journey, delivery to the asphalt mixing plants. The modified bitumen is transferred from the reactor into insulated storage tanks which maintain its temperature at around 175 degrees. In this liquid state, it remains perfectly uniform. It is then pumped through high-pressure sealed pipelines to the nearby plant or loaded into road tankers with special thermal containers. These tankers are built with a double-skinned steel body and a thick insulating layer. The drivers undergo special training. They must maintain a steady speed and monitor temperature sensors in real time. If the temperature begins to drop, an onboard heating system activates. At the plant, for example, the DXB asphalt factory in Dubai Industrial City, the tanker connects to the intake system. At this moment, the bitumen is hot, thick, and has a distinctive smell. It is pumped into the plant's holding tanks, where it waits to be precisely dosed. From this point on, it is no longer just a material. It is a component in a formula, where the weight, viscosity, and temperature of every ingredient will determine the lifespan of the road it is destined to become. One of the largest plants is the DXB asphalt factory. Here, the bitumen is heated to 160 degrees and mixed with mineral aggregates, gabbro, basalt, and quartz sand. Gabbro is a dark volcanic rock quarried in the mountains of Fujairah. The rock is crushed into fractions smaller than 25 millimeters, screened through vibrating sieves, dried in huge rotating drums, and then fed into the mixer. Inside, the bitumen and aggregates are combined into a hot, uniform mass known as hot mix asphalt. The temperature of the mix is 160 degrees. It must be perfectly homogeneous, with a precise ratio of components. After mixing, the asphalt is transferred to insulated silos where it can be stored for no more than 6 hours. From there, it is loaded into insulated trucks for the final journey. On site, the asphalt is laid by paving machines and then compacted by rollers, first vibratory, then static. In the desert, achieving maximum density is critical to prevent the ingress of sand and water. Compaction is done in multiple passes, and the temperature of the asphalt must not drop below 120 degrees Celsius during the process. If it does, the mix loses its workability and the road's integrity is compromised. A key feature of Dubai's highways is their multi-layered structure. The base course is made of a coarse-grain asphalt. The middle, or binder course, uses the modified bitumen and acts as a shock absorber. The top, or wearing course, is a thin layer with a high polymer content to provide grip and durability. In some cases, reflective minerals are added to reduce heat absorption. In the desert, it's not just the heat. Dust, wind, and humidity changes all have an impact. Asphalt plants in Dubai are equipped with advanced air filtration systems, and the mixes themselves are tested for resistance to abrasive wear and thermal expansion. In the RTA's laboratories, every batch of asphalt is checked for viscosity, density, and thermal stability. If it fails to meet the standards, the entire batch is rejected. This journey, from oil tanker to finished highway, takes several days, but involves dozens of quality control stages. And it is because of this meticulous process that Dubai's roads can withstand the daily punishment from thousands of vehicles without melting under the desert sun. Over 1 million tons of asphalt are produced in Dubai annually, and this figure is growing with the city's infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, allowing it to supply major projects without interruption. For comparison, an average plant in Europe produces around 150 tons per hour. Interestingly, asphalt is the most recycled material in the USA, with over 99% of old pavement being reused. Dubai is also actively adopting recycling, especially during the reconstruction of older highways.
Pick up a stone. Bright red, heavy, looking like dried blood. It doesn't smell, doesn't burn, doesn't radiate. Just a beautiful mineral. Now throw it into a furnace at 1300 degrees Fahrenheit, and liquid metal flows out. Silvery, heavy, cold to the touch. The only metal on Earth that stays liquid at room temperature. Mercury, a substance that has mesmerized alchemists for millennia, poisoned kings, and powered industry. And it's extracted from a stone that looks like a gemstone, but is actually just ordinary sulfide. Today, we're at a mine and processing plant where red rock turns into liquid silver. If you're into deep dives like this, subscribe and hit the bell so you don't miss new episodes. This red rock is called cinnabar, mercury sulfide, one of the few natural compounds where mercury shows up in Earth's crust. The chemical formula is simple: 1 mercury atom, 1 sulfur atom. Basically, nature locked liquid metal inside a sulfur cage, and to get it out, you've got to break that cage with heat. If you crack a chunk of cinnabar, the fracture surface reveals crystals with a diamond-like shine. The beauty's deceptive because the powder from this mineral is poisonous. Cinnabar was known even in ancient times. Egyptians used it as pigment, Romans painted palace walls with it, and Chinese alchemists believed the red ore was the key to immortality. Deposits are scattered across the planet, but the main ones are in Spain, Slovenia, China, and Kyrgyzstan. The Spanish mine at Almaden operated for nearly 2,000 years and gave the world more than a third of all mercury ever extracted. The ore sits in volcanic activity zones because mercury rises with hot solutions from deep within Earth's crust and settles in rock fractures as bright red veins. Sometimes cinnabar is so rich that the rock looks like someone painted it with scarlet dye. Mining starts underground. Miners drill into the rock with pneumatic jackhammers, place charges, and blast, bringing the whole face down. They load the ore into mine cars and haul it to the surface. It's hard, dangerous work. Even down in the mine, mercury vapor seeps from the rock, so ventilation runs at full blast. Mercury content in the ore is usually low, 1 to 12%. The rest is waste rock, sandstone, clay, quartz. But even 1% is worth going after because mercury fetches a high price. At the surface, the ore gets crushed in jaw crushers. 2 steel jaws squeeze the rock, breaking it down to gravel size. Then, vibrating screens sort the pieces by size. The fines go straight to the furnace. Oversized chunks loop back for another round of crushing. Dust is a whole other problem. It carries mercury, and breathing it is dangerous. So the crushing plant runs heavy exhaust and wet dust suppression.
Workers wear respirators, and at the entrance, there's a mercury vapor monitor. If the needle swings into the red, they shut down the plant and air it out. Now comes the most critical step, roasting. The principle is simple yet brilliant. Heat cinnabar to 1100 to 1300 degrees Fahrenheit in air, and the sulfur bonds with oxygen and escapes as sulfur dioxide gas, while the mercury vaporizes. Two substances locked in stone for millions of years part ways forever, one into the air, the other into a pipe. Roasting furnaces come in different designs, but the classic is a rotary kiln. Picture a massive steel drum, 60 to 100 feet long, set at a slight angle. Ore gets fed in from the upper end, burners fire from the lower. The heat inside is so intense, the furnace walls glow a dull cherry red. The kiln rotates slowly, tumbling the ore, gradually pushing it downward as it heats up more and more. When the temperature hits the sweet spot, the cinnabar breaks down. Sulfur burns with a bluish flame, and mercury vapor, invisible and deadly, rises and travels with the flue gases into the condensation system. The spent rock, now stripped of mercury, spills out the lower end of the furnace into a waste pile, gray, lifeless, having surrendered everything valuable to the fire. Condensation is the moment when invisible vapor transforms into that actual liquid metal. Gases from the furnace pass through a long system of pipes and chambers that gradually cool down, usually with water fed through jackets on the outside. Mercury condenses first. Its boiling point is only 675 degrees Fahrenheit, so when the gases cool below that mark, silvery droplets start settling on the condenser walls. They trickle downward and collect in receivers, steel or ceramic containers. The sight is mesmerizing. From the pipe, as if from nowhere, heavy silvery liquid drips down, falling into the collector with a distinctive, soft sound. Not a clang, not a thud, but something in between. Because mercury is viscous and heavy, 13.5 times heavier than water. A quart of mercury weighs more than 28 pounds. Try picturing a quart of milk that weighs as much as a bucket of cement. The raw mercury from the condenser isn't ready for sale yet. It's swimming with impurities, soot particles, water droplets, traces of other metals. It's cleaned in several stages. First, they filter it through chamois leather or special fabric. Mercury passes through the pores while the dirt stays behind. Then, they wash it with diluted nitric acid, which dissolves impurities like zinc, lead, and tin, leaving the mercury itself untouched. The final purification is vacuum distillation. Mercury gets heated in a vacuum, where it evaporates at a lower temperature, while impurities with higher boiling points remain at the bottom. They collect the condensate, and now you've got mercury at 99.9% purity. It's poured into standard steel flasks holding 76 pounds. That's the international standard called a flask. The container's small, about the size of a thermos, but lifting it one-handed? Not easy. All because of that incredible density. Safety at a mercury plant is a world unto itself. Mercury vapor has no color and no smell, but it's extremely toxic. Just a few hours of breathing it can give you serious poisoning. Chronic exposure destroys the nervous system. That's why hatters in the 19th century went mad. They used mercury to treat felt and inhaled the fumes for years, hence the phrase, mad as a hatter. In a modern plant, the entire facility operates under negative pressure. Air is constantly pulled inward, not pushed outward, so vapors don't escape into the atmosphere. Floors are coated with a special non-porous covering. If mercury spills, the droplets won't roll into cracks, but stay on the surface where they can be collected with a specialized vacuum or a sulfur trap. Sulfur powder binds mercury into harmless sulfide. Every worker carries a personal dosimeter that measures accumulated vapor exposure per shift. Exceed the limit, and you're pulled off the floor until your levels normalize. Where does all this mercury go?
Historically, the biggest consumer was gold mining. Mercury dissolves gold, forming an amalgam. You then heat it up, and the gold evaporates out. Conquistadors in South America used this method, and it's exactly why the Spanish crown exploited almaden for centuries. Today, amalgamation is officially banned in most countries because of the catastrophic environmental damage. But in artisanal mining across Africa and Southeast Asia, millions of prospectors still use it. Poisoning rivers, poisoning soil. Other applications: chlor-alkali industry, thermometers, barometers, mercury lamps, electrical switches, catalysts. But the world is slowly moving away from mercury. In 2013, the Minamata Convention was signed, named after a Japanese city where, in the 1950s, thousands of people suffered devastating poisoning. Mercury leaked into the bay from a chemical plant. It built up in fish. And the people who ate that fish started losing their sight, their hearing, their coordination. The Minamata tragedy became a symbol of mercury pollution for decades to come. Mercury production worldwide is plummeting. Back in the mid-20th century, mines pulled out up to 10,000 tons a year. Now, less than 2,000. Most mines have shut down. The famous Almadine in Spain stopped operations and turned into a museum. These days, mercury increasingly comes from recycling, old thermometers, lamps, industrial waste. But humanity can't completely abandon it yet. Some chemical and electrochemical processes simply have no substitute. When you stand next to a flask where this heavy, silvery liquid sloshes around, it's hard to believe that an hour ago it was part of a red rock that sat underground for millions of years. Cinnabar guarded mercury like a safe guards valuables, and only fire could pick that lock. An ancient process, simple at its core, dangerous in execution, and still without an alternative.
Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears. Yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory, this is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine. a 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between two rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees, so the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms. Internal stresses build up. Keep rolling without annealing? The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill, that's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat, 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the microtexture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between 2 chambers. Helium under pressure is fed into one. A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil wins onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity, 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible.
Every year, over 100,000 kilometers of new railway tracks are laid worldwide, enough to circle the Earth several times. But few people stop to think about how a perfectly straight strip of steel, capable of withstanding the weight of multi-ton trains and speeds of over 300 kilometers per hour, is born from a piece of scrap metal. Inside furnaces, the temperature reaches 1,500 degrees Celsius. Molten metal flows like solar lava, and precision is measured down to tenths of a millimeter. And most importantly, there is a secret here that is rarely shown publicly. If you watch until the end, you'll learn this secret that allows rails to last for decades without a single joint.
First, a steel mixture needs to be made. Scrap metal, iron ore, coke, and limestone, the raw materials that will become the future rail, are fed into the furnace. The temperature in a blast furnace reaches over 2,732 degrees Fahrenheit. Under this infernal heat, the metal becomes liquid, acquiring the color of the red-hot sun. Workers carefully monitor the composition. Even an extra 0.1% of carbon can make the rail brittle or too soft. After melting, the molten steel is poured into molds, metal ingot molds that form rectangular blocks called ingots or slabs. They don't yet look like a rail, they are just bars several meters long, over 30 centimeters wide. After pouring, each such blank is cooled, but not completely. It is kept warm to reduce the load during rolling.
This stage is the foundation of everything. If the steel is of poor quality, even perfect rolling won't save the situation. So control here is almost a ritual. Chemists check the composition, metallurgists control the temperature, and automatic sensors record the uniformity of cooling. And only when everything matches down to the last parameter is the blank sent further, into the fiery furnace of the rolling mill. In the rolling mill, massive bars, up to 20 meters long, are heated in furnaces to a temperature of over 1,200 degrees Celsius. The metal becomes plastic, like dough, but retains its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce the thickness, then to give it the correct shape.
Each pass involves compressing and stretching the metal, which gradually transforms from a simple bar into a future rail with a complex cross-sectional profile, with a head, a web, and a foot. To achieve precise geometry, finish calibration rolling is used. This is like the final polishing of the shape. The tolerances at this stage do not exceed 0.3 of a millimeter. Immediately after rolling, the rails, still hot, undergo a cooling process. They are evenly blown with air or left to cool in an open area. It is important that the cooling is symmetrical, otherwise the metal may warp. To ensure a smooth, impact-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding.
In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture, formed as a result of the reaction of powdered aluminum with iron oxide. The temperature reaches as high as 2,500 degrees Celsius, is poured there. This melt penetrates both parts of the rail and envelops the joint zone. When it solidifies, a monolithic joint is formed, stronger than the rail itself. After this, the excess metal is cut off, and the weld site is ground to a perfectly level surface without any protrusions. Every joint is inspected with ultrasound or eddy currents so that no hidden microcracks remain. Such long rails are easier to transport than it seems. They are wound onto special drums or transported on platforms with swivel nodes.
And at the construction site, the sections are joined again, this time by welding or using special bolt joints. The result is a rail string that stretches for kilometers without a single click. The same silent glide that we are used to taking for granted on high-speed trains. But first, after rolling and welding, the rails are still alive. Stresses remain inside the metal and the grain structure needs stabilization. This is where heat treatment comes into play, which gives the rail strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, about 1,832 degrees Fahrenheit. This is done in furnaces up to tens of meters long, where the temperature is controlled with degree precision. At this point, the crystal lattice of the steel transitions to a new state, austenitic. But the main part begins after.
The rail is instantly cooled. Jets of water under high pressure are directed along the head and web, the very part on which the wheel rolls. The temperature drops in a flash, and a martensitic structure forms in the metal, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled again. This balances the structure, relieves excess internal stresses, and ensures that the rail will withstand both frost and heat, and thousands of trains a day. As a result, the metal holds its shape and withstands a pressure of tens of tons per square inch without deforming. Before the rail hits the road, it goes through a whole series of rigorous tests, as if it wants to join the army of high-speed transport. In special laboratories, it is tested for strength, hardness, geometry, and internal defect.
First, ultrasonic inspection. High-frequency waves are sent into the rail. If there is a microcrack or a void somewhere inside, the signal is reflected and reveals the problem. Then, hardness measurement along the entire length to ensure that the heat treatment was uniform. In parallel, the straightness and profile are checked. Laser sensors scan every inch, detecting even minor curvatures that could cause vibration or wear. And finally, a bending and impact test. A fragment of the rail is loaded with a pressure tens of times greater than the weight of a train to make sure it will withstand any challenges on the route. When the rail has successfully passed all the tests, it's time for the most responsible journey to the installation site.
But how do you transport giant metal strips over 90 meters long? Ordinary trucks can't handle it. Here, special railway platforms with curved supports are used, which reduce stress and prevent the rail from sagging or vibrating during movement. Sometimes rails are transported already welded into even longer sections of 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is necessary to compensate for the thermal expansion and contraction of the metal. Otherwise, in the heat, it will buckle, and in the cold, gaps will form. In practice, each rail is laid taking into account these physical changes. Usually, this is a point of no thermal stress.
What if I told you the world's toughest roads and roofs aren't born on the construction site, but deep inside oil's blazing heart? A material that survives 360-degree heat and brutal cold. One mistake by the technologist, it turns to stone. But why did this black, sticky residue at the bottom of the oil column become the backbone of bridges, airfields, and massive warehouses? And what chemical secret lets it survive for decades without cracking under 40-ton trucks? Every year, the world produces hundreds of millions of tons of bitumen. It's extracted at temperatures between 930 and 1200 degrees Fahrenheit, squeezing literally the last drops from crude oil. Roofing felt? It passes through vats of molten bitumen at 570 degrees, where every inch of cardboard or fiberglass gets soaked in black gold. One wrong step in the process, and within a couple winters, that road's covered in ruts and potholes. Stick around till the end. You'll discover what even some manufacturers won't tell you.
Picture a massive oil refinery. Giant distillation towers, tall as a 20-story building. Crude oil flows in and gets heated to 650 to 750 degrees Fahrenheit. Fractional distillation begins. Light fractions, gasoline, kerosene, vaporize and rise upward. Middle fractions, diesel, fuel oil, remain in the center. And at the bottom of the tower, a heavy tail accumulates, thick, dark residue. This isn't bitumen yet, but it's already the base for it. This residue goes to a vacuum column. There, it's heated again, but under vacuum, at reduced pressure. This allows even more fractions to evaporate, which become lubricating oils and paraffins, without pushing the temperature high enough to break down the heavy molecules. What remains after this squeezing out of the heaviest parts, that's the foundation for bitumen and tars. But it's still a raw product. Next, chemistry kicks in. Into enormous reactors, they load this residue and add other components. For example, light oils, polymers, modifiers, sometimes sulfur.
At temperatures between 500 and 650 degrees, the mixture is held so large organic molecules partially cross-link, becoming more viscous and heat-resistant. Complex chemical reactions occur: oxidation, polymerization, condensation. Hydrocarbon molecules unite into even larger and heavier structures. The result is a thick, extremely sticky material that becomes solid or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close cousin of tar, but with a clear focus on road construction and roofing. It's also derived from heavy petroleum residues after vacuum distillation. In large bitumen plants, it's less about pure chemistry and more about fine-tuning viscosity and temperature behavior. If the bitumen is too hard, it'll crack in winter. If it's too soft, it'll run in the heat at 200 degrees on the asphalt.
That's why the technology has a concept called penetration, how deep a needle enters a sample at a given temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymer modifiers to get a material that won't flow in the heat and won't turn brittle in the cold. In massive mixers, bitumen is heated to temperatures from 450 to 650 degrees Fahrenheit, and under intense mixing, they add modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airfields, bridge expansion joints. When people say asphalt road, they actually mean a mix of mineral materials, crushed stone, sand, mineral powder, with bitumen as the binder.
In huge asphalt mixers, the crushed stone is pre-dried and heated to temperatures close to 570 degrees Fahrenheit to ensure there's no moisture.
Then hot bitumen gets added and mixed until every single pebble is coated in a thin film of binder. The hot mix heads into dump trucks, then straight to the job site for paving. Get the bitumen wrong? A few seasons later, you're looking at ruts, cracks, and potholes. Nail the process? That pavement will handle years of trucks weighing dozens of tons. Roofing felt. It's the story of turning a simple roll of backing into a durable shield against rain, UV rays, and temperature swings. The base is cardboard, fiberglass cloth, or a polyester mesh in roll form, roughly 3 feet wide. Cardboard backing gets picked for budget materials and light-duty jobs, fiberglass when you need better heat resistance and less warping, and polyester for flexible roofs where stretch and tear resistance matter. All these backings share one trait: they're porous, so without treatment they soak up water easily and fall apart fast. To turn a bare base into waterproofing material, the roll gets run through a processing line with vats of hot bitumen or bitumen resin compounds. The liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to lower viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the vat so that it's completely submerged in the melt and passes through at a controlled speed. During this time, bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the vat, excess material is removed by calibrating rollers. This helps maintain the specified thickness and avoid drips. Next comes the stage of forming the coating layers. The saturated base passes under bitumen or resin applicators that apply the main layer on the bottom and top. For this, knife or roller coaters are used. A thin gap between the roller and support measures out the coating thickness.
The bottom layer handles adhesion to the roof deck or foundation, so it can contain more elastic plasticizers, polymers, oils, special additives that reduce the risk of cracking during bending and temperature swings. The top layer acts as armor against sun, rain, hail, and physical damage, so it's made harder and more heat resistant, sometimes modified with polymers for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules. A dispenser on the line drops a steady stream of mica, basalt granules, or slate onto the moving belt. The particles instantly press into the soft bitumen and lock in place as it cools. This coating isn't just for nice rough texture, it works as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower and doesn't crack as fast. Plus, the granules boost abrasion resistance.
After the granules are applied, the sheet moves through a cooling zone. This uses either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial that the temperature drops to a safe level before winding into rolls. If you roll up hot material, the layers stick together, the geometry gets thrown off, and the granules can lose adhesion. To monitor parameters on the line, they install temperature sensors and thickness gauges that ensure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt sheet is cut lengthwise or crosswise into standard rolls, most often between 30 and 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the upper layers don't slip. Sometimes, one side is left with a strip without granules, covered with pure bitumen.
When laying, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't stop you from heating with a torch. Polyethylene or paper liners get added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the type of base, the weight of bitumen per square yard, the type of surfacing, the flexibility temperature, and other specs that matter to designers and installers. The story doesn't end there though, because how roofing felt behaves on a roof depends heavily on what exactly got mixed into it back at the factory. If you take regular oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where the surface easily heats up to 360 degrees in summer, that layer gradually loses elasticity, becomes hard and brittle. To prevent that, polymers get added to the binder. Polymer modifiers make the material more flexible in cold weather and better at handling high heat. Roll roofing can easily withstand both winter freezes and summer scorching without developing a spiderweb of cracks. It's polymer modifiers that gave Roofu Felt new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several 100,000 square feet. The classic setup: leveled substrate, a layer of primer from bitumen emulsion, then several layers of roll material with a 4-inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the substrate. The top layer goes down the same way, forming a continuous blanket, where the seams are the most critical zones. The quality of that seam determines whether the roof leaks or not. And so, traveling from the bottom of an oil column, through vacuum distillation, through heating to 1200 degrees and oxidation, through vats of molten bitumen at 570 degrees, through coating with mineral granules and cooling, a material is born that protects millions of buildings from rain and snow, withstands 356 degrees of heat and minus 22 degrees of cold, serving for decades without a single crack.
Imagine a part so perfect it can spin for 30 years without stopping. From tiny balls just 1/8 of an inch across to giants 30 feet tall holding up wind turbines, bearings are a $120 billion a year industry. But their life begins in absolute chaos. Massive explosions, hellish fire, pressure that could crush a tank. How does raw metal become the heart of perfection? Today you'll follow the complete journey, from a quarry blast to the perfect ball spinning at 10,000 revolutions per minute. If you want to see how chaos turns into precision, subscribe to the channel. Here we show the manufacturing that builds our world. It all starts with a roar that shakes the ground for miles around. In the giant quarries of Australia and Brazil, iron ore hides in layers of rock hundreds of feet thick. Geologists turn the quarry into a chessboard. They drill boreholes 60 to 100 feet deep. Borehole diameter, 10 inches. Distance between boreholes, 16 feet. 1 square mile, 1,000 boreholes. Into each they pour explosives, a mix of ammonium nitrate and diesel fuel. Ratio 94 to 6%. Charge weight per borehole, 650 pounds. Detonation happens with millisecond delays. First borehole explodes. 20 milliseconds later, the second. 40 milliseconds, the third. The wave rolls across the entire field. In 10 seconds, they detonate 200 boreholes. They blast 3.5 million cubic feet of rock, energy equivalent to 110,000 pounds of TNT. But this isn't random chaos. This is planned destruction. Chunks of rock shoot 150 feet into the air. They fall. Dust rises over half a mile into the sky. When it settles, instead of a mountain, there lies 2 million tons of crushed ore. Giant excavators roll onto the site. The excavator bucket? 1,400 cubic feet. That's the volume of a small apartment. The bucket weighs 28 tons. One scoop? 100 tons of rock. They load it into dump trucks. Hauling capacity of each truck, 360 tons. Wheel height, 13 feet. Diameter, 11.5 feet. Weight of one wheel, 5 tons. Engine, 3,500 horsepower. Fuel consumption, 35 gallons per mile. The dump truck hauls ore to the crusher. Distance, 9 miles. Speed, 25 miles per hour. Travel time, 20 minutes. In one day, a single truck makes 30 trips, hauls 10,000 tons. 20 excavators and 60 dump trucks work the quarry. They move 300,000 tons of ore per day. That's 100 million tons a year. Crushing. Ore enters the jaw crusher. The crusher's mouth, 13 feet wide. The jaw weighs 120 tons. Jaw stroke, 12 inches. Oscillation frequency, 200 strikes per minute. Drive power, 1.5 megawatts. The crusher pulverizes yard-wide rocks into 8-inch chunks. Throughput, 2,000 tons per hour. From the jaw crusher, ore moves to the cone crusher. The cone spins inside the bowl at 150 revolutions per minute. Gap between cone and bowl, 1 inch. 8-inch pieces become 1-inch pieces. Then the ball mill. Cylinder 20 feet in diameter. Length 26 feet. Inside steel balls. Ball diameter 4 inches. Weight per ball 9 pounds. Total balls 50,000. Combined weight 200 tons. The mill rotates at 18 revolutions per minute. Balls drop from 6.5 feet. Impact grinds ore to powder. Particle size after milling 0.04 inches. The thickness of a human hair. Thickness. Flotation enrichment. Ore powder gets mixed with water, creates a slurry. Solid concentration, 30%. Add reagents. Potassium xanthate, 7 ounces per ton of ore. Pine oil, 1.8 ounces per ton. Xanthate makes iron particles hydrophobic. They repel water. Pour the slurry into the flotation machine. Tank volume, 13,000 gallons. Air pumps in from below. Pressure, 30 pounds per square inch. Flow rate, 10,000 cubic feet per hour. Air forms billions of bubbles 0.2 inches across. Bubbles stick to iron particles. Lift them up. Foam forms on the surface. Reddish gray. Dense. Iron content in the foam, 67%. Waste rock sinks to the bottom. Gets pumped out and dumped in tailings. Foam scraped off with blades, sent to filtration. Vacuum filter sucks out the water. Leaves a damp mass. Moisture content, 9%. That's concentrate. Gets turned into pellets. Pelletizing. The concentrate goes to a disc pelletizer. The disc is 15 feet across. Tilted at 45 degrees. Spins at 15 revolutions per minute. Powder feeds onto the disc. Water's added, 3% by weight. Centrifugal force rolls the powder into balls. Pellets come out 1/2 inch in diameter, give or take 1/16 of an inch. The pellets roll off the edge onto a conveyor. Output? 300 tons an hour. 1 million pellets every hour. The pellets head to the kiln. Firing temperature, 2450 degrees Fahrenheit. 20 minutes in the heat. The pellets turn rock hard. Crushing strength, 3,500 psi. Now they're ready for the blast furnace. Blast furnace smelting. Pellets are loaded into the blast furnace. The furnace stands 105 feet tall. The throat diameter, 40 feet. The hearth diameter, 26 feet. Furnace volume, 42,000 cubic feet. Loaded in layers. Pellet layer, 3 feet. Coke layer, 20 inches. Limestone layer, 8 inches. Hot air blasts in from below. Temperature, 2,200 degrees. Pressure, 60 pounds per square inch. Flow rate, 100,000 cubic feet per minute. The coke burns, carbon monoxide releases. It strips the iron from the pellets. Temperature in the hearth, 3600 degrees. The iron melts, flows downward, pools in the hearth. Every 4 hours they tap the pig iron. They open the tap hole. Pig iron pours out like a river of fire. Temperature at 2700 degrees. Color, bright orange. One tap, 300 tons. In 24 hours, the furnace produces 2,000 tons of pig iron. The pig iron contains 4% carbon. That's way too much. Pig iron's brittle. Needs converter smelting. Steel production. They pour pig iron into an oxygen converter. The converter holds 350 tons. A lance descends from above. The lance is 20 inches across. Pure oxygen blasts through the lance. Pressure hits 175 pounds per square inch. Flow rate, 18,000 cubic feet per minute. Jet velocity, 1,300 miles per hour. That's twice the speed of sound. Oxygen oxidizes the carbon burns. Turns into carbon dioxide. Flame shoots out the converter's mouth. Flame reaches 30 feet high. Temperature hits 3,600 degrees. The process takes 20 minutes. Carbon content drops from 4% down to 0.7%. This is bearing steel. Grade designation SAE 52100. Chromium content 1.5%. Chromium provides hardness and wear resistance. They pour the steel into a ladle. From the ladle into molds. Out come ingots, blanks weighing 5 tons each. Ingot dimensions, 3 feet by 3 feet by 6 feet. Rolling and machining. Ingots are heated in a furnace to 2,200 degrees Fahrenheit. Rolled on a mill. Rollers 40 inches in diameter. Rolling force 2,000 tons. The ingot becomes rods 4 inches across. Rod length 20 feet. Rods are cut into blanks 8 inches long. Blanks are heated to 1,560 degrees. Stamped into rings on a press generating 1,200 tons of force. You get a ring with an outer diameter of 4 inches. Inner diameter, 3.1 inches. Height, 0.8 inches. Rings undergo heat treatment. Heated to 1,540 degrees. Held 30 minutes. Quenched in oil at 140 degrees. Cooling rate, 540 degrees per second. Tempered at 360 degrees for 2 hours. Hardness after heat treatment, 62 Rockwell. Then, grinding. The ring is clamped in a lathe chuck. The abrasive wheel spins at 100 feet per second. Removes a metal layer 0.004 inches thick per pass. Surface roughness, 0.08 millionths of an inch. That's 10 times smoother than glass. Deviation from roundness, no more than 0.08 thousandths of an inch. Balls are made by cold heading. Wire 1/2 inch in diameter is cut into 1/2 inch segments. Each segment is clamped between 2 dies. Pressure, 2 tons. The segment deforms into a sphere. You get a rough ball, it's ground between 2 cast iron discs. The discs rotate toward each other. Speed, 200 revolutions per minute. Between the discs, abrasive paste. Grit size, 40 micrometers. Grinding takes an hour. The ball shrinks by 0.012 inches. Final diameter, 0.46 inches. Deviation, plus or minus 0.004 hundredths of an inch. Sphericity, 0.08 thousandths. Roughness, 0.02 millionths of an inch. Bearing assembly. Inner ring, outer ring, 17 balls. Brass separator, lithium grease. Bearings done. It'll spin for 30 years, 1 billion revolutions.